Hello, good morning, everybody. I hope that you had a pleasant night after the very busy day yesterday. So today we have only half a day, and then we will let it go 1 year more. And we start in a session where we will see a few of the Chief JU competence centers, mostly related to photonics, I would say, presenting today. So we have 4 of them. And the first one is Big Spain Competence Center that is represented by Robert Jalir from the University of Malaga. So please, Robert.
Thank you. Okay, so thank you everybody for coming so early in the morning, and welcome to this session on competence centers. So first of all, thank you, Pascual, for introducing me. My name is Robert. I'm from the University of Malaga, and I'm here today to talk about the PIC Spain Competence Center. Now, just to make things very clear, even though I'm from the University of Malaga, this is actually led, the competence center is led by Pascual over there, right, at the University of Valencia. The Competence Center is composed of these 6 partners. So apart from the University of Valencia, it's Malaga, ICFO in Barcelona, our National Center for Microelectronics, the University Carlos III in Madrid, and the University of Vigo. All right. So here's the outline of my talk today. For those who are not familiar with Malaga, I'm going to give you a short introduction to what's going on in terms of photonics in Malaga. I'm going to provide you some broader context on photonics initiatives both in Europe and locally here in Spain, and only then will I focus on the Competence Center. Part of the Competence Center goals is to train people, and I want to focus on that a little bit more in my last session training activities. Okay, so let's dive into it. This is the photonics group in Malaga. So we're about 25 people, several senior professors. Our IP is Inigo. You probably know Gonzalo, Alejandro. You've met them at conferences around the world. And we also work very closely with Pavel. Pavel is from Canada, but we have a very close link with him. So as a group, what do we do? Well, we've been designing and testing photonic integrated circuits for almost 2 decades now, and let's say our specialization is in making devices, photonic devices that work really, really well. We are probably best known for work on sub-wavelength metamaterials, which are these nanostructured waveguides that allow you to tune the optical properties of silicon waveguides mainly, and make very nice devices with this. Okay, what's going on in Malaga apart from the research at our group? Well, we're starting to see what we call an ecosystem. It's actually a very small ecosystem, but well, there it is. This moved around. So apart from our group, we now have 2 spin-offs. One is called Bioherent, and what they do is in vitro diagnostic with photonic sensors. And another one, which is more recent, which is called AG Photonics, is developing integrated transceivers for FSO, right? So we're trying to build this ecosystem where we actually can transfer some research from the university to those companies, and well, hopefully create value with it, right? Another important thing, and you can write that down in your calendar if you have it on hand, is that ECOC 2026 will be held in Malaga. It is jointly organized by the University of Valencia, so the chairs are Professor Capmani and Professor Molina from the University of Malaga, and the technical program chairs will be myself and Ivana. I don't know if she's around. She was certainly yesterday. So that will be September 2026. All right, unrelated to our group, but still a lot on the news is that IMEC is starting a clean room in Malaga, right? So apparently all the paperwork is done, and we're all expectant for it to start, right? The idea that they say what they're going to do is they will start to work on non-standard processes, right? This includes of course both electronics and photonics. So people ask me, do you know what they are going to do at IMEC in Malaga? And no, I don't, right? So I don't. But I'm still sure it will be a good push for photonics in our region. Okay, so with that bit of knowledge about Malaga, let's have a look at what photonics initiatives are going on and how they are possibly related with the Competence Center. So we already had a few sessions yesterday on the JIPS joint undertaking, right? So you probably already know all about it. The main goal here is to accelerate semiconductor technologies in the economy, right? That's mainly digital technologies, electronics, but also photonics. And, well, you know, there are these pilot lines that are meant for rapid prototyping and also for companies to start on a small scale to produce some more chips, right, on a slightly larger scale than just prototyping. In terms of photonics, and that was also discussed in detail yesterday, we have this PIX Europe pilot line, right, which is also coordinated from Spain, and which will push photonics technology along several lines, right, and hopefully, well, have more industry pick this technology up. All right, apart from that European initiative, we have a Spanish initiative which is called the PERTE Chip, right? So this is a flagship program within Spain which is designed for the same purpose as the CHIPS JU under JU Act, and the idea is that it should restart, let's say, microelectronic development in Spain. So focusing just on the photonics part, not on all of the microelectronics, but just on the photonics part, there are a few of these PERTE chip chairs. One is in Madrid, in the Polytechnical University together with Indra, and the photonics part they're doing there is mostly focused towards microwave techniques. We have the Carlos III University in Madrid, who will be dealing with packaging. The cathode chip at the UPC, together with ICFO, is very focused on quantum. We have the activities here in Valencia, right? So there is programmable photonics, there's some sensing, there's LiDAR. We have Vigo University, who will be working mainly on testing. And we have Malaga Microelectronics, which has a small part devoted for photonics, right? So let me just, since I'm from Malaga, let me just give you a bit more detail on Malaga Microelectronics, right? So of course, all of these, what they do is industry-oriented research, but they also have a strong focus on education, right? Because you cannot have industry take off if you don't have the people, well, to do the work. So Malaga Microelectronics is a 5 million euro project. Most of it goes to analog and digital electronics, but there's a slice of it that's divided to photonics, right? So in the digital domain, it's mostly VLSI for IoT and imaging. In the analog domain, it's RF, microwaves, millimeter waves, mainly for communications. And in silicon photonics, well, it's aligned with the activity of our two startups, which are in sensing and in free space optical communications. In terms of education, there will be a master in microelectronics, so that's a rather long master program. I think it's a bit more than a year. But we're also starting some micro-credentials in integrated photonics. So we'll talk about these a little bit later on in the talk. All right, so how is all this related to the competence center? Well, we say, okay, with the JIPS JU, we want industry to use more digital technologies, more semiconductor technology, more photonics, because we hope they will become more competitive in that way. So we have quite a few actors that have to come together, right? So on the one hand, you have industry, conventional industry, that can potentially leverage photonics. Okay, so that's one thing. Then you have students, right, or future talent, call it what you want, but you will need people to do these jobs, right? We have, of course, the pilot line and the design platforms. We have university and research organizations. And, well, we have the money, right? We have capital who has to provide funding to startups, right? Or, well, it has to flow somehow into this industry, right? So you have these 5 things, and all on their own, they don't converge, right? They don't start suddenly to seamlessly work together. So this is where the competence center comes in, right? Think of it as kind of a catalyzer that brings these things together. So in the case of the PIC Spain Competence Center, again, this is led by UPV, University of Valencia, and Pascual. The idea is something like this, right? So you can think of the competence center like an interface, right, or a catalyzer between users, right? So these can be enterprises, research organizations, and so on. European stakeholders like the CHIPS JU Act, right? And what we want to do is we want these users here, right, to have access to these technologies, to the new technologies offered here, and we want to help them use them and, well, make a profit of them. So in our case, this is organized along 5 main goals, right, which are the CHIPS, the connection with the CHIPS JU training, connecting enterprises with the technology, some focus on industry, as well as the pilot lines. So let's go, before we go into detail in each of these 5 points, let's see who is PIC Spain. So PIC Spain is these 6 partners. So I'm sorry, this slide is extremely crowded, but let's just go through it. So the leader here is Universidad Politécnica de Valencia, right? Well, you all know people from Valencia. They have clean rooms here, and they also have a few startups, right? Actually, Ipronics is probably already starting to be a bit more than a startup, right? So they have a good experience in transferring research results into the market, right? We have CNM, which is the Center for Microelectronics, right? They have a clean room, and they are developing silicon nitride technologies. We have ICFO, which is, well, I think it's well known around the world, probably in photonics for their work on quantum, right? There again, they have a number of startups. So again, they're well positioned to transfer research into into a more industrial environment. We have the University of Malaga down here. So we are fabless, right? So we don't have our own clean room. But again, we have quite a bit of experience in designing photonics and also in transferring it to industry with these 2 startups. We have the Universidad Carlos III in Madrid, again, with a startup, Leapwave, right? And Vigo, which is also working with a startup. So it's kind of a set of universities that are well positioned in photonics, but not only on the research side, but also on the knowledge transfer side. So these are the groups or the universities that make up the competence center here in Spain. Okay, so I think of the competence center as a matchmaker, right? As somebody who connects entities. So what are our matchmaking activities? Well, the first one is to keep a fluent connection with CHIPS.ju, right? Our European colleagues from the competence centers, which are here, luckily today, with the design platforms and so on, right? So this will be mainly driven by the University of Valencia. At the University of Malaga, we will be focusing on training and workforce development. Again, this is key, right? Because you can convince many industries to pick up photonics, but if they can't hire people to actually make it happen, it's going to be useless, right? Technological advisory for end users. So this will be run by CNN, right? Which is part of the Spanish CSIC, the Research Council. So here the idea is that if you find a company that says, hey, yes, I would like to, I don't know, make a sensor with this photonic technology, but they don't know the technology. So you have to somehow get them started, right? You have to teach them. You have to give them advice. So this will be the role or this will be the objective here. The University Carlos III in Madrid will be focused on ecosystems. What do we mean by ecosystems? Well, you have to get together people from industry, but you also have to get capital, right? You have to get venture capital. You have to engage with the public institutions, right? You have to develop roadmaps, and you have to see how this all fits together, right? So this rather complicated thing is up to UC3M, right? And finally, ICFO will be focusing on bringing people into the pilot lines, right? So how do you get companies to actually use those pilot lines? How can you help them access? How can you help them? How can you explain them what are the services, what are the advantages, and so on. All right, so these are the main goals for our competence center. I would now like to talk a little bit about training, right? That's, well, just because Malaga will be focusing on this activity, right? So what kind of training can you already get in Spain in photonics, right? And I'm focusing here specifically on integrated photonics, and I hope I'm not forgetting any alternative. If I do, please raise your hand and correct me, okay? So the University of Valencia has a master in photonics integration, which is actually associated with the PERTA chip chair. The Polytechnical University of Catalonia, together with ICFO, has a long-standing master program in photonics, right? So these are relatively long programs, between 1 and 2 years. The University of Vigo is going to develop micro-credentials focused mainly on photonic testing, right? Of course, the span is a bit broader than that. We have the University of Carlos III in Madrid with assembly and packaging. And in Malaga, we're about to start micro-credentials in photonic devices. Why photonic devices? Well, because that's what we do best, right? So what are these micro-credentials about? Oh, sorry, I forgot something. The Polytechnical University in Madrid also has a master in photonics, right? So for me, it's important to distinguish a bit between these master programs and the micro-credentials, right? Master programs are for students, right? Or mainly for students, right? Because they have to come here, they spend the better part of a year doing conventional training in a master's, right? Micro-credentials are not better or not worse than masters, different people, right? Or they serve a bit of a different purpose. The idea here is that you can take like a mini course condensed in time that gives you instant expertise in a very specific topic, right? And you might want to string several of them together, right? So the micro-credentials are much better suited for somebody who is already in the field, right, and who needs some extra training. So these programs don't really, I don't think they compete with each other, right? They offer training in similar topics, but to people with very different needs. Okay, so that being said, let's have a quick look at what a micro-credential programs can look like. And I'm going to use the UMA example, of course, because that's the one I know most about. So the way we're going to be organizing is that each course lasts only 2 weeks, but it's very intense, right? It's 15 hours per week. We will do it in the afternoon, and we will try to do it mainly online, right? So again, that's for people who are already in a different job and they need training on this, right? So we will have a first week, which will be mainly concepts and fundamentals, and a second week, which will be more hands-on, right? So using a software, doing some designs, or heading to a lab. These are subsidized by the per-to-chip program, right? So they can be potentially free for the students. What people do we want, or what people do we think can enter this? We think it's important that you have a background in engineering, right? So you need to know some math and physics. So if you come from chemistry or mathematics, you can probably also do them. What kind of courses are we going to be organizing? There's a little QR code here if you're really interested. It takes you to the website. Again, the idea of micro-credentials is that you get very specific knowledge on one topic, right? So for us, it's these 9. I'm not going to go through all of them, right? But of course, we start with optical waveguides, right? So just something really on the fundamentals for somebody who's new to the field, right? But you can then immediately jump to more advanced stuff if you want, right? If you want to become the best grating designer in the world, well, you do periodic dielectric structures. If you want to do microwave photonics, well, here you do microwave photonics. On the other hand, you're interested in quantum, so you go for quantum, right? So it's really, you can choose what you need, right? And you get a very concentrated dose of knowledge in little time. If you do all of them, then you're a very brave person, and you get a diploma in specialization diploma in integrated photonics. So these micro-credentials, they're already running in some other places. In our case, we're starting in May. Enrollment starts in April, right? So you can have a look at these. All right. So what messages would I like you to take home with you to remember? Well, yesterday there was a bit of discussion if it's a question of push or pull in photonics, right? That's always going to be a discussion, of course. I think from our side, from the universities, from the research organizations, it's definitely our time to push, right? So hopefully somebody will pull on the other side, but for us, it's time to push. What can the competence centers do? Well, if we do our job well, we will catalyze things, we will push things forward, we will connect people, right? Both in training, funding, the pilot lines, commercial interests, and so on. And well, if you have any questions, here's my email, and there's Pasquale's email. So feel free to contact us. And yeah, that's all. Thank you very much for your attention.
Thank you, Robert, for the nice presentation. Is there any question? I should not be the one making the questions, right? So, because
it's very early, Pasquale.
This is very much related to me.
About the micro-credentials that you mentioned, what kind of background they are expecting to have? Kind of bachelor students, master
Yeah.
students, PhD
So
students?
we are
okay.
trying to keep it relatively basic,
Okay.
right? But you will have to have some sort of degree in engineering, right? So if you're an industrial engineer and you haven't forgotten your math, you should be able to do it, right? If you're a physicist, I think you're in a superb position to do it. If you've done chemistry, well, you'll have to polish up on your math, right? If you're a pure mathematician, I think you can probably do it, but you will, yeah, like your skin will itch a little bit, right? When we violate the different theorems, right? Yeah, I think that's the idea. I mean, our experience, frankly, is we can take our bachelor students, our third-year bachelor students, the good ones, and we can teach them this stuff. Because we do it when they do their final year projects with us, right? Their trabajos fin de grado and these things, right? So I think it's definitely possible. You don't need to have a master's before doing this, but you need to have some formal training in math, essentially.
Okay. Thank you very much.
Any other question?
Thank you, Khalid, for the presentation. I wanted to ask you about these courses, if it's mandatory to be in situ in Malaga.
No, well, the way we are doing it, because as I said before, we think micro-credentials are for a specific type of person, right? So we understand they're probably already doing something else, right? So we want to keep it online when possible, right? So as I said, the first week is going to be always taught online, right? And in English, of course. For the second week, we would encourage people to try to come, right? It's 3 days of a week, right? So it's a few afternoons well spent, right? Because we really feel that when you're sitting in front of a simulator and you're having some trouble, or you're trying to align a chip and you're not getting there, trying to align the chip is actually only possible if you're physically there, right? But even if you're working on a tricky problem, it's easier if you can be there, right? So we would encourage people for the second week, would encourage them to come. Can you do it online? Yes, in most subjects, in others not, right? I think there is this subject here, characterization of silicon photonics chips. No, you can't not come, right? It's obvious, right? For the others, we'll try our best to make it accessible.
Hi, hello, thank you for the presentation. I was wondering about if there is a maximum number of participation or participants for these micro-credentials.
We're not yet 100% sure, but probably yes. Yeah. Probably yes. So it's going to be around 10-ish or so, we think, right?
Okay.
Depends a bit on how the funding works, right? But yeah, there's going to be a limit. But I mean, hopefully our problem is that we have too many applicants, and then we'll have to think about something for the next year, right?
Okay, and then I think that you don't mention about this. You put in the slide is subsidized this kind of credential, so it's for free. This kind of
for a limited number of people, yes.
Okay.
So we still have to figure out the exact numbers.
Okay. Thank you.
Thank you very much for the presentation. It gives a very nice overview of Big Spain Competence Center.
Thank you.
I have a question about your vision for the collaboration with other competence centers in Europe.
Okay, that's a good question, which I should probably not answer because Pasquale is in a much better position to do that.
I don't have the right answer right now because we are starting, so we will need to figure it out down the road. Good thing is that we have already established connections with, for instance, your group, and that we're establishing new connections with people coming to this event, and we're probably gonna get to know each other in the events, and see how can we cooperate. It's a very abstract answer, I know it.
No, but definitely I would like to have a talk with you and you the guy from Norway? Where's the guy from? There's the guy. Sorry. So we should have a little talk, exchange emails, and at least for the person we are going to hire, one of his or her tasks will be getting in touch with people from other competence centers, right? Because we won't solve all the problems within the boundaries of this beautiful country, right? This is a very European challenge, right? And I think we're well aware that we have to cooperate and that will be very beneficial. Still very abstract, sorry.
Okay, so we will thank Robert again and move to the next speaker. Thank you. So next speaker is Alfonso Gavarrón from ASMI, la Asociación Española para la Industria de Semiconductores. Please come.
Okay, so here we are. Okay, it's moving. Okay. Is it? Are we going to have that? Okay. Okay. Thank you very much. Good morning. I am Alfonso Gavarrón. I am the general manager of ASMI, the Spanish Semiconductor Industry Association. And I'm going to introduce you the second competence center that is going to be in Spain. In Spain, due to the characteristics of our ecosystem, we're going to have two. One, as you have seen, mainly focused on photonics. And then we have another one which we are leading, which is a bit more transversal, and it's aligned with the PERTE chip pillars on quantum microelectronics, also photonics. So we will cover up a bit of everything. So you are saying, well, I'm going to skip the context on the competence centers because I am assuming that with the presentation that Robert just did, you already know that what a competence center is. Okay, so a competence center. So competence centers are a key part of the European Chips Act schema, because they need to be in the middle of everything, of the pilot lines, the design platforms, the users, the training activities. So hence we are starting working together with several partners in Spain to develop a new entity that could cover all these activities. Thank you. Have I done something wrong? Okay, so it's, yeah. So who is actually belonging to Micro Nano Spain, which is our competence center? Well, we have a core consortia based from CNM. We are including the three centers that they have in Spain, Barcelona, Seville, and Madrid. We are also including the Barcelona Supercomputing Center, and we are including three universities, the Polytechnic of Madrid, Polytechnic of Valencia, and Polytechnic of Catalonia. This is the core consortium. But as you can see, most of these entities do belong into an existing network called Micro Nano Fabs, which is a unique platform for accessing services from different entities. So that's the root of a competence center. That's why we are calling Micro Nano Spain, because it's an extension of the actual model of Micro Nano Fabs. And for that extension, we are counting with a lot of partners, as you can see here. We have more than 20 in the in the project, and that's covering other associations, that's covering institutes, RTOs, universities, and even some private companies. Our approach is to be very inclusive, as you will see now, and be able to showcase all the services that can be delivered in the Spanish ecosystem. So, how are we approaching the competence center? We started working through 3 pillars. The pillar 1 was to have a single platform where you could find and access all the services for design and fabrication on semiconductors in Spain. And that means not only finding the information about who can provide which services, but also contract that service through the platform. Think about some kind of Amazon, where a company can find who can provide some fabrication services for them, contract them, and access then directly those activities in their facilities. But in this pillar, we will also include the services that are being delivered through other European initiatives like the pilot lines and the design platform. Then we have a second pillar, which is focused on workforce development, where we will present all the training ecosystem that there is in Spain, and again, we will help people find their way through their more than 50 universities that are currently in Spain, and understand which differences are between each master, each university, each PhD, etc., etc. And then we will also have a third pillar for boosting the ecosystem with more with some kind of venture builder activities, with also ensuring that companies can access public and private funding, etc., etc. So let me get into a bit of detail of this. So through the pillar 1, what capabilities are we planning to include into these platforms? As you have seen, the core of the consortia is micro nano fabs, so we plan to take as a basis the existing platform. We will also include the services that pilot lines will be providing, as soon as we know how to include them, because that's still something that we need to discuss. We will include services that are currently being offered by universities. And here I am not just meaning, for example, here in the Polytechnic of Valencia, we have the NTC, or we have the UPV Fab. If there is research group in a certain university that provides design services, or that can provide also some kind of characterization service or testing service through equipment that they got in the past, that will also be accessible. We are doing this because we are seeing that through a lot of European funding and national funding, we have developed a very vast ecosystem in Spain of capabilities that right now are being underused. Because simply some of the research projects that are being done in the universities don't require the a full use of those equipment. So we want to open them to the ecosystem. We will also include capabilities from R&D centers, from other design centers that are in Spain, and from private entities also, especially meaning those that have been awarded with the IPCIs that need to be open to the ecosystem. Again, our approach is to ensure that all capabilities that need to be accessible to a startup, to an SME, is accessible through this single portal. And what are we going to do with that information? First of all, we will provide guidance services, just to ensure that companies or universities understand the requirements of the projects, and that they can find the correct partner. As Robert said, competence centers are matchmakers, so we need to help them find the correct partner. We will provide the access itself to the capability. Our expectation is to have is to let the companies even do the contractual aspect of that access through the same platform, and that meaning that you don't need to sign an agreement with the university. The competence center in the back will be working with the one who's providing the service to ensure that the administrative field is covered, but we want to make as quick as possible for a company the access to any kind of service in Spain. We will have a pool of experts that are going to be accessible for providing technical advisory services and consulting services. And we also open the door for providing other services, some kind of bureau practice, but with other technical services and also services that can be open to different entities, SMEs, startups, etc. But that's not, we don't have a full list of those other services that we will be providing. That's just to open the door in case if it's necessary. So this is the pillar one. As you are seeing, it's complex because we are planning to create a whole new entity in Spain, like a whole new institution that can reunite all the players in the ecosystem that are providing services and can manage and access to their service portfolio externally. So that's even legally, it's a super complex model, but we are really hoping that we can make this through. The second pillar, as I was saying, is based on workforce development, and here we will do the same. We will have that platform that can handle all the information from the training ecosystem. What kind of trainings will be accessible through the platform, both public and private, and that means bachelor, master's, PhD, micro-credential, other certificates that can be provided through universities, but also courses that maybe Synopsys and Cadence can offer. In fact, we are already working with these providers to have their training catalog to ensure that it is accessible through this platform. So how are we going to manage this? For public training, we will just showcase the information and then redirect you to the university page. In case of private-owned training, it depends on what the owner wants us to do. We can just redirect the user to the training provider, or we can host the training ourselves. And in those cases, and only in those cases where we are seeing that there is a gap between what the industry is requiring in terms of training, the competence centers will be providing its own training, mainly focused on clean room technicians, operators, things like that. We are planning to cover the gap which is below universities and vocational trainings, to have that cohort of people who is right now lacking of specialized training for microelectronics and semiconductors, and get them on board for the ecosystem. And we will also include a job board just to make it accessible for everybody. And then the pillar 3, which is again more oriented to dynamizing the ecosystem. We are planning to have a venture builder in collaboration with CDTI. You saw yesterday a talk about Invierte. Well, they are already developing their own venture builder, and we will be working with them to develop an ad hoc program to help startups on the sector. We will also launch an open innovation lab, which will connect demands from large players in Spain with these startups. And by large players, we are meaning to have connections with leaders in certain fields, like telecommunications, textile, aerospace and defense, and let them propose directly to those startups what do they need. And we will also have a pledge fund, which is a pool for attracting private investment. So it will be an extension of the Invierte program, but only targeting semiconductors. And through this pillar, we will also do a lot of other things for outreach and awareness, connection with other competence centers, etc., etc. What are even if you have seen a lot of players at the very beginning, we are planning to include more, because we did had a lot of requests when we were developing the proposal, and we didn't include everybody at the very beginning, because managing a consortia of all these people is complex. So we will open the door in the near future, as soon as this is working, to other entities, both public and private, to include their services through the platform. We will have a special focus to include all universities that are willing to provide their services, especially those that are a participant of the chip chairs. And we will also open the database. So in case, for example, an autonomous region wants to have their own platform for accessing their local services, we will also make that available. In fact, we are working with a couple governments to have that kind of repository of local services. Because that's the key of success, opening as much as we can to include as much players as we can, and have as many users accessing the platform. So this is an introduction of the proposal. I have not gone to concrete examples of training programs, etc., because as you have seen, this is wide enough. But more than happy to discuss or answer any questions that you may have. Of course, we do have a lot of work together, because we do need to align on how we'll be providing access to services, and also to not be repeating activities, because a competence center is A, B, C, and D. So we need to see how we can split things together. But it is good to see that we are already having a very good relationship between our competence centers. So that's all from my side. Open for questions.
Thank you, Alfonso. Questions?
Thank you very much for your presentation. I have a question regarding this central portal, and you invite the, let's say, service providers to list their offers. What was the last slide?
Okay.
I'm wondering if it's just at the national level, or you're open as well to European scale?
We are already working with some European skill initiatives, for example, with the European Chip Skills Academy, and we are also part of a couple other initiatives on the European Alliance on processors, which is also working on skills, and we are also developing another parallel project with other national clusters of other countries to develop a unique skill platform. So our expectation is to connect with other regions, but we are still seeing how are going to develop their own training initiatives. But yeah, the expectation is to open the database to as much information as we can, at least on the training portfolio. On the services, we will only include national services, because if we were to include services being provided by an entity in France, we will be covering the France Competence Center activity. But for the training portfolio, we are open to exchange information.
Any other question? No, so then we will thank Alfonso again. Move to next speaker. So next speaker is Christopher Andrew Dierdal from Sintef. and who will be presenting the Competence Center from Norway.
Thank you. All right, thank you very much. It's a pleasure to be here in Valencia and seeing all the optimism around the photonics industry. I go home to Norway very motivated. So today, as mentioned, my name is Christopher Dirdal, and I represent the Norwegian Chips Competence Center. It's still early days. We haven't figured out all the details, but I'm here to present a little bit of the background. So CC Nordchip, a Norwegian Competence Center for Semiconductors, Chips and Sensors, securing and bolstering Norway's position in advanced technology. So this is an overview of the current situation of chips in Norway. In the left column, you'll see an overview of the research environments involved. We have, for example, the university in Tromsø, UiT, the Arctic University of Norway, where they are working quite a lot with integrated photonics. And then we have the 4 nodes of Norfab, which is Norway's national infrastructure on nanotechnologies and microtechnologies. In the second column, we have those that actually produce chips. We have Safran, which used to be called Sensonor until recently. They work a lot in MEMS-based sensors for IMUs and accelerometers for commercial and military applications. And then there's SINTEF, which is an independent research institute that has a R&D and pilot line for small-scale production. I'll get back to SINTEF later on. The third column, we have the users of chips that are made in Norway. For example, MEMSCAP, that creates pressure sensors for the aviation industry. There's around 250,000 planes and helicopters that have these sensors that are actually made by SINTEF and then integrated by MEMSCAP. There's a big chance that you've flown with our sensors. And then there's also various other industries, also SMEs that use chips in Norway. And then in the fourth column, we have the fabless chip suppliers. And this is actually a very big aspect. Nordic Semiconductors, that is mentioned here, is actually Europe's largest fabless chips designer or producer. They have their Bluetooth chips in almost everything, headsets, mobile phones, and so on. And of course, that's where a lot of the money lies. And then in the last column are examples of integrators that use the chips. So a couple of years ago, there's a lot of people trying to raise awareness on the semiconductor industry in Norway. We don't only make fish and petroleum. And it's an interesting trend, actually. Over the last years, the amount of people working in the semiconductor industry has doubled. In the same period, the value creation has quadrupled. So this is a highly productive industry with significant growth, with a turnover of around $1 billion US. There's a strong ecosystem of SMEs and startups, and there are strong research environments. And then there are also players in all of the areas around the chips as well. So yes, a lot of people, when they think of Norway, they think of petroleum, they think of fish, but I think they should think about chips as well. If you compare, I like this graph, if you compare the yearly growth in value creation, the semiconductor industry in Norway actually competes with the petroleum industry and the fishing industry. So Norway should talk about its fish and chips, not to be confused with what they eat in Britain. All right, so this is the background for the Norwegian Chips Competence Center. The partners in the Competence Center are listed here. We have UiT, the Arctic University of Norway, today represented in the audience as well with Olav. And then there's SINTEF, which is coordinating the Chips Competence Center. And then we also have partners NTNU in the city of Trondheim, the University of Oslo, and the University of Southeastern Norway, and an industry alliance called the Electronic Coast. So, and our competence center covers a wide range of different types of chips, primarily in sensing. But since we're here in Valencia, I'm going to talk specifically about our interests in integrated photonics. So I start with the UiT, the Arctic University of Norway. Dr. Olav Gaute Hellesø is in the audience. He provided me with this picture. I hope this is not the actual travel itinerary you took to get here, because it would take around 51 hours to drive. If you did, I'm sure there's a lot of people who could hitch a ride back home because you're going through all of Europe on the way back. But the university in Tromsø, within photonics, they have 6 professors and principal investigators, around 30 postdocs, PhDs, and technologists. They've secured 7.5 million euros for validation and commercialization since 2023, which is very good for a Norwegian university. And they work heavily in sensors and chip-based microscopy. And I'm going to show 2 examples of this. The first one is photonic chip-based multimodal optical nanoscopy. This activity is led by Dr. Balpreet Ahluwalia, who I think has some collaborations in Spain already. What he and his group is trying to do is to take a very complicated microscope and replace it with a very simple one by using integrated photonics. So instead of using these lab chips for your biological samples, replace that instead with a chip of waveguides for illuminating the sample, and then use simple collection optics afterwards. And this technology allows you then to get super resolution images, very, very wide area images. And this technology is currently being commercialized by a company called Chip Nano Imaging. The second activity that I'd like to draw attention to is led by Dr. Jana Jagashka, who is using waveguide-based platforms for gas sensing. Norway has quite a long tradition with gas sensing, related to measuring hydrocarbons offshore, for example. And this is a very interesting platform. It gives a very good sensitivity. Okay, so I should probably have talked even more about what is going on in the far north, but I shift to my organization, which is SINTEF, which is it's an organization of 2,200 employees. Unfortunately, not all in microelectronics, where it covers basically what Norway does in energy and materials and so on. But we do have a sensor department of 100 people, where we work a lot with photonic technologies. So SINTEF Minelab, it's a combined research and development and innovation and industrial small-scale production pilot line for 6-inch wafers. We produce for around 40 customers annually, and our customers are in aviation, scientific tools, medical, and offshore industries. We've, for example, delivered 300,000 altimeters for pressure sensors in aviation, 180,000 radiation detectors for various scientific tools, 250,000 IR sources for gas detection, and we've been making photodiodes for 60 years. And our facility is very geared towards commercialization, so over the last 20 years, we've had around 9 chip technology startups that have come out. Since we're a small-scale pilot line, we are ISO certified, and we're also a Euro practice provider of thin-film piezoelectrics. So this is the one side of our activities, the production side. As mentioned, aviation, pressure sensors, radiation detectors, and gas monitoring. But the more interesting side of it, I think, is the technologies that we take to market. Recently, the latest success story is the one on the top right. Spin Chip Diagnostics was sold for a couple of weeks ago to a French medtech company for, I think, 160 million euros. By the time that happened, our share in the company had been so diluted that we don't get that much of the money, but it's a success story. On the left-hand side is our optical technologies that have been taken to the market. Gas Secure developed a diffractive-based gas sensor. Tunable is making a MEMS-based Fabry-Perot interferometer, an optical cavity for gas detection. Polite is a company that makes tunable lenses that actually bend the surface of a chip so that it becomes like a refractive lens. And Sensibel is a company that interferometrically reads out the position of a membrane, so it's an optical microphone. All of these are free space applications. and we are now very interested in integrated photonics. Traditionally, what we develop at Sintef tends to get to market in the future, and we see a lot of interest in integrated photonics. So we've been working with material platforms for many years. We've been working with MEMS for many years, but recently we've hired people from integrated photonics, and we're interested in these aspects, or these are niche aspects where we think we can contribute. So we are interested in making integrated photonics adaptive. We have a long track record in MEMS, and that's our angle into that. But we're also interested in extending the bandwidth of the waveguides. So you see a picture of blue light, for example. So we're interested in material systems to go into UV. We have 60 years of photodetector fabrication and production, so we're also interested in the possibility of integrating detectors with photonic integrated circuits. And then on the research level, we've been quite interested in this topic of metasurfaces, nanostructures to manipulate light for couplers, but also spatial mode manipulations on chip. So these are the four interest areas we have. So just briefly a bit on each. So in terms of active modulators, on the right-hand side you can see a picture of our MEMS modulators for PIC. The way that these work, this is more of a proof of concept, but we take our thin film piezoelectrics and deposit them on top of a cladded waveguide, and then we liberate the membrane so that you can, by applying a voltage to it, you can bend it and you can extend the path length, but also introduce strain into it. This gives you very strong modulations on a short scale. It's not very fast because a membrane bridge you can't vibrate that at gigahertz. So there's a trade-off, but it's a very similar platform to what, for example, Ionics is working on. And we have 20 years experience with these materials. We also, from the MEMS side, we've been interested in aluminum nitride for a very long time. And recently now we're interested in it for the photonic integrated circuits. This is a material, of course, that has a very wide transmission window. It has a higher refractive index than aluminum oxide, but it also, and in addition, it has the piezoelectric effect and an electro-optic effect. So it's a very interesting material, but so far it's been a material with a lot of losses. But together with the University of Oslo, who have many years experience with working with nitrides, this is the next sort of research level platform that we're interested in. We also have some collaborations using PCT, this lead zirconide titanate material, together with plasmonics for making couplers in plasmonics. Okay, so that was the active PIC. When we look at the passive PIC, we've been using aluminum oxide as a passivation layer for our MEMS for many, many years. And then when we hired a new person who wanted to make waveguides with it, we tried that. And we actually have a quite good platform for aluminum oxide with low loss. And we're interested in pushing this into the UV. We have an established collaboration with the University of Tromsø and this company Chip Nanoimaging, who uses these chips to illuminate biological samples and then get this super resolution imaging. So these images are created by using aluminum oxide waveguides and collecting it through simple microscope. We're pushing PIC into the UV means that, of course, sizes scale down, and we have the capacity to do submicron patterning. We've been working a lot in the area of metasurface optics, so we have scalable patterning capabilities using nanoimprint, for example, and we also recently purchased a maskless aligner and grayscale tool from Heidelberg. Just a couple of slides on also detectors. We've been making photodetectors for 60 years, primarily for radiation detection, meaning that the detectors are a bit thicker than they otherwise would be. They've, for example, been used in the CERN experiments and in various synchrotron facilities around the world. I don't think I'll go into too much detail on that, but we have some various applications on that. And we are coordinating a European project called Compass, where the goal is to integrate both the waveguides, the detectors, and the light source on a single chip, and also have analog IC on the back end to analyze the data. The idea is that you have a very compact sensor for air and water monitoring based on integrated photonics. I will move forward to my last set of slides. We've been working a lot with these meta surfaces over the years, but this has only been done primarily for free space things. You can see on the right-hand side these arrays of nanostructures, typically used to make lenses, but you can combine them with MEMS to make interesting things like tunable lenses, tunable polarizers. You can control the orbital angle and momentum states of light, and so on. These are things that we've been doing in free space, but we are also interested in looking at using them together with integrated photonics. Couplers, high efficiency couplers is an obvious thing, but it's also interesting to kind of modulate the spatial modes of light on a chip. I know that in Barcelona you've worked a lot with these bimodal waveguides, for example, and it could be interesting to look into things that you can do with this as well. We're also coordinating a Pathfinder project using this platform for modulating free space light. All right, so just to summarize, we've just started with our CHIPS Competence Center, and we don't have all the details, but we have a strong interest in connecting to Europe in integrated photonics, and it's been a pleasure to see all that is going on here, and I hope to stay in touch. Thank you very much.
Thank you, Christopher, for your nice presentation. Questions for Christopher? You guys definitely need coffee. Come on, one break, one. Okay, there were two then.
Thank you very much. This is David from BLC Photonics. Regarding this aluminum oxide platform you mentioned, is there any open access initiatives in Norway, like MPW offerings or any sort of open access?
I don't think we've formally done it, but SINTEF as an organization is of course open for this, and I don't know if that answers your question, but we don't at the moment have any PDKs or anything like this, so we would more collaborate as a research organization on it. But our roadmap into the future is to develop PDKs, and we are part of the next pilot line initiatives on quantum things and stuff like this. So the ambition is to provide this platform openly to Europe. Yeah.
Okay, thank you. I have a few questions regarding your fab capabilities. I mean, you mentioned it's a 6-inch facility, right? What is the capacity of it? Is it just a R&D, or can you do pilot production? Like, how many wafers a year can you handle? A second follow-up to that is that, what are your capabilities in terms of lithography? Like, for example, do you use stepper DUVs or eye lines? I saw a MLA mask, like maskless, right? But what else of capabilities do you have?
Yes, thank you very much. So we are a small-scale pilot line. So we do MEMS fabrication for customers. So, for example, MEMSCAP, who deliver for the aviation industry, we make their chips. I think we've never tested actually what is our top capacity. That we always have room for more, but I think on the order of 10,000 wafers per year is what some people say. Yes, 6-inch. But we've never kind of pushed ourselves to being a serious production lab. We are an R&D lab first and foremost. But it's organized as a pilot line, so we have dedicated engineers on each tool and stuff like this. So it's the PhDs and postdocs don't have access to the tools. So it's run like a production lab, but it's an R&D and innovation lab as well. In terms of our patterning capabilities, the Heidelberg and the nano imprint tool that I showed are our best or the best resolution tools. So with Heidelberg, we have the high resolution option that gives us line widths down to around 300 nanometers, I think. And with the nano imprint, it's limited by the electron beam lithography mask that you can purchase, right? So it's on the order of sub-100 nanometer resolution for this. Yeah.
Okay, thank you. Last question here, maybe.
So thank you very much for your talk, and I was blissfully, or not so blissfully, unaware of SINTEF. So
You said it's a private research organization, so how do I think of this? Like Fraunhofer Institutes in Germany, maybe something like this?
Yeah, independent, non-profit. We 90% of our budget we have to get in competition through EU funding, national funding, but also a big part of it is in industrial contracts. I think we're more comparable to VTT in Finland, although Fraunhofer is a similar concept. I think Fraunhofer has a higher degree of basic funding than us. Yeah.
Okay, thank you.
Okay. Any other question, maybe? No? So let's thank Christopher again, and let's move to the next speaker. So the next, last speaker for the session is Katia Panina from JEPIX and the Eindhoven University of Technology.
Thank you very much. It's a great pleasure to be here today. Thank you very much, Pascal, for inviting me. Today, I have the honor to present the ChipNL. This is a Dutch competence center. And we just started off the 1st of January, so it's as well very early stage, but it's well, I will give you an overview what we've been up to and the ecosystem in photonics. So first, I will start with an overview of the national agenda in the Netherlands. Netherlands is a relatively small country. It's just 1/3 of population of Spain and 1/10 area of Spain. But despite this fact, the government realizes that the importance of semiconductors, and we have quite vibrant ecosystem in the Netherlands. So there is a national semiconductor strategy, and there is a ChipNL innovation program, which is led by more than 60 companies and knowledge organizations, and we do have such big players as SML, ISM, and Xperia, Philips, and Signify. And this program is to boost the chip machine construction and chip design and packaging in the Netherlands. On the other hand, the talent is a problem everywhere in semiconductor ecosystem in general. So there is a huge investment with Operation Beethoven that is to address the shortage of technically trained personnel, and this is more than, well, approximately half a billion euros dedicated to knowledge institutions to develop actually training programs. This is not only for the university and students and masters, but it's really for upskilling, reskilling, and long life learning programs. And finally, there are several national growth funds being launched by the government, and one of them is particularly dedicated to photonics, National Growth Fund Photon Delta program, and it's basically to support economic and ecosystem development, particularly in photonics. So, of course, let's say this landscape was quite vibrant, but of course the national has to link to European, because we are a player of much, our contribution is much more important on European level as well. So the national strategy has to connect to the European one, and therefore we look at the synergies with the European Chips Act and the different funding schemes, and Competence Center, of course, it just makes sense to be part of the bigger national strategy as well. So when we were defining the goal for the Competence Center in the Netherlands, there are two ways how to approach this question. This is to look at the competence that the Netherlands has and wants to offer to the rest of Europe, versus expertise that the Netherlands wants to develop. So the first one is expertise that the Netherlands thought that we are really good at. We have a very strong semiconductor manufacturing equipment ecosystem with ASML, of course. And therefore, this is one focus area of the competence center in the Netherlands to actually share the knowledge about manufacturing equipment for semiconductors. Then the coordinator, Brainport Development, made, they went outside to different companies in the Netherlands and asked, what competence would you like to develop? And the answer was that the companies would like to develop skills in chip design. And under chip design, we have different focus areas. It's electronics, of course, but also photonics, quantum, and heterogeneous integration. So about the focus areas, similarly to the previous speakers, our competence center has a similar structure. First is we offer technology services, and well, we do not invent things, but it's more like really create an overview of what we already have and connecting the dots on the national scale. So we do have supply chain coordinators in our competence center, and we build a network of these offers on the national and international level. So Tino is leading the supply chain for the manufacturing equipment. IMEC is leading chip design and electronics. And JPEX that I'm representing today is leading, let's say, a zoo of exotic, how sometimes people define the technologies, photonics, heterogeneous integration, and quantum photonics chips. Then for us, it's important to inform and influence application markets. There will be, we will be supporting the team of business developers that will go to companies working on specific applications and raise the question whether they considered chips before, or so we will engage in active, let's say, scouting with the companies, and the supply chain managers are there to help to answer technical questions. And to start with, we identified the application markets as automotive, industrial, energy, health, smart city, communication infrastructure. Also, technology services are there to provide access to the chips GU pilot lines and design platform. Of course, the synergy is very important. So it's a matchmaking exercise, and we need for that the central organization to actually support users to navigate this complex European landscape. Also, it's access to European network of competence centers, because we realize that, well, Netherlands might be great, but we are just part of much bigger picture, and that's why we are looking at the players all over Europe, how we can find complementary services, because we do not believe that just the Netherlands can answer all the questions that our startups and SMEs have, and that's why we are looking at the other competence centers in other countries to actually map all the capabilities in Europe. Finally, it's a knowledge dissemination between knowledge institutes and industry. We also have a very big part dedicated to business growth. Talent is one of those, and it's important to connect what is necessary in the industry to learn about chip design or equipment, and connected to the education providers. So for this, we are linking to the Operation Beethoven. And as well, we look at other European skills initiatives. And again, synergies with other players in Europe are key. Also, we have the Accelerator program, which is to provide this support to startups. This is a connection to funding, for example, just explaining the landscape, what is out there, whether those are European projects or national funds or investors. So, and also going really out there and explore well, push the boundaries, not only technology, but as well understand the needs of the markets in different domains and translate it to technology, of course. Of course, we do have the promotion work package there as well. There will be a big part of internalization and, of course, the marketing communications and events. And I do really appreciate being here today. So that's as well very nice first step to connect. The project officially started as of January this year, and well, we have already the LinkedIn page, so please feel free to connect. We are planning a national kickoff event or events, because even though the Netherlands is a small country, but we have different regions, and every region wants to have their own kickoff. So there will be events, I think, somewhere around April or May later this year. These are the partners in our competence center. So Oostenel is here. They are basically our business developers that will push the technology and help us understand the market needs. ChipTech 20, they are the coordinators and, well, innovators in our representatives when they talk to small enterprises and startups in the Netherlands. And High-Tech NL and Brain is responsible for communications. Brainport and Dovan is basically the coordinator of the project. And Tino, IMEC, and JPEX, we are the supply chain managers. So, if to sum up, the overall objective of CHIP NL Competence Center is to be internationally recognizable and effective entry point for companies, particularly SMEs, startups, and scale-ups seeking expertise and support, which are provided through provision of services, whilst at the same time contributing to the strengthening of the Dutch expertise in areas of semiconductor manufacturing equipment, chip design, heterogeneous integration, and facilitating access to this knowledge. So pretty much in line with other competence centers that presented before me, I would like to stress here the importance of being internationally recognizable. And that's because we are in Europe, and in Europe we have 5 pilot lines so far. The Quantum One or Quantum Ones are coming. And so far there have been launched 27 competence centers and at least 4 more coming. So this is going to be a very challenging exercise to connect the dots and understand what capabilities we have in Europe as a whole, not just on the national level. So if I zoom in photonics in the Netherlands, we are not starting from zero, and I'm happy that we are not starting from the national level either. We are starting with a European platform for manufacturing of photonic integrated circuits. It's open access platform JPEX that started in 2006. We have a very long track record supporting more than 150 companies worldwide. And manufacturing, supporting about 1,500 designs just on MPW, multi-project wafer runs. We provide open access services in photonics, where you get access to the quality state-of-art facilities in Europe. We also support with the knowledge. We have training programs and organized technology forums, and with the goal to skill up the workforce and as well to connect and develop the ecosystem. Ecosystem development in terms of roadmap and future evolution of markets. We have this very big exercise on road mapping, the JPEX roadmap and as well the international IPSRI roadmap. And finally, this is technology acceleration, because we are very active in advancing technology through the standards. That's the overview of the commercial supply chain of JPEX. These are 19 industrial partners, well coordinated historically by TUI because we started as a European project in 2006. It's not a commercial, it's not an entity, it's not a legal entity, it's simply the collaboration between industrial companies, not because they just feel alike or they offer photonic services, but the benefit here that the services are interoperable. So we align on the same standards and methods, how we exchange the data, how we validate the data. So we build a supply chain together. And none of these offers are freestanding. We have foundries as the core of our offer, and this is access to 3.5 platforms offered by Smart Photonics, Fraunhofer HHI 3.5 Lab, so European foundries with native lasers, and silicon nitride foundries like Lyonix and Ligentech. Cornerstone has recently joined JPEX as well, and TUI as well offers a very crazy research playground there. We do have software tools in the ecosystem, also packaging, design house, and tests, so basically covering the whole supply chain in photonic integrated circuits. The linear prototyping with JPEX looks like that we start with the orientation, then we look at the application that the users want to develop. We support with peak design, fabrication, test, and finally our users can have the prototype. So it's important to underline that all the services are available, interoperable. You know upfront what the prices are, so we already reduce the barriers to the companies that want to start doing photonic integrated circuits, basically by making things clear how much it will cost to get the first prototype in terms of money, in terms of time, in terms of investment. We'll help with the choice of suppliers at every step. Interoperability here is key. You can really configure your supply chain based on your demand, and that's how we lower the barrier for the new designers. All the foundries are offering multi-project wafer runs. So this is the concept of building blocks, where you have a pre-calibrated generic process, which is, however, very powerful, has a large library of components. And you do not have to think about a non-recurring engineering course, because this is a mature process that's shared by multiple users, and therefore it reduces really the barrier to start doing prototyping. We do not limit ourselves with prototyping, but we have as well the pilot production, and our suppliers can go to, well, some volume, depending, of course, on the type of the foundry you're working with. And the benefits is that, again, we offer a pre-qualified manufacturing process that you do not need to pay for customization very much. You can see whether your design makes sense, and study the manufacturability of your design, and move towards multiple dedicated full wafers, and then think about customization if it's really necessary. And we also offer the training, the Peak Design course. It's a deep dive training that was originated, I think, in 2008, so we have very long track record. It is a 2-week annual format at TUI, and it offers a very nice blend between the theoretical knowledge and hands-on. Our users, our trainees, they go to the clean room, do some processing there. They go to the measurement lab and get the light out of the chip. And also they have the opportunity to try, I think, 4 different software tools and decide for themselves what is best. And the goal here is that after these 2 weeks, you are already able to design your own chip. And even though it's primarily was developed for PhD students,
It was as well very popular with our industrial customers. Even though 2 weeks is a very long format for industry typically, that's why they invited us to develop a shorter format, which is a 2-day course. And we are running this twice a year. That really doesn't contain hands-on, but gives really the overview of photonic ecosystem and how to get started with the design, with the product development, and what are the necessary steps towards actually industrialization. So if you are interested, these are the dates. We have just closed the concept training, the 2 days. So peak concept training is a 2-day format, while peak design course is an extended version. Both are held in Eindhoven. So if you are interested, I'll see you in Eindhoven in October. Also, we share our knowledge in the way which is a very, very nice one. I'm very proud of this. Coming soon, in the coming weeks, I would say. This is a handbook for generic indium phosphide-based peak design that is developed, is written by JPEX partners and University of Eindhoven staff. These are the 30 chapters that cover the physics and technology, basic building blocks, the composite building blocks and circuits. And this book will be simply published on JPEX website, and anyone who wants to start doing photonic integration, they can go there, read that, and we make this knowledge available. So I think that's really great that we can remove the barriers this way. To sum up, I think that we are building from the national, but we need to think that it's part of European. So of course, we need to create a comprehensive picture of what we have in Europe as a whole, and while starting with the outline of capabilities and supply chains on the national level and national demands of the competence center, we want to expand to the European level to see what other players in Europe, what other competence centers, the pilot lines and design platform have to offer in terms of design capabilities, technology access, suppliers, training programs, and funding opportunities, simply to know how we can support national startups and national talent in the best way. And I do believe that the strength is in the complementarity of our offers, and together we can really build a big puzzle. And this type of projects is exactly where the total result is a sum of many. And we do not always have the best fit in technology skills and competences, but it's important to know where we can find them. So thank you very much for your attention, and if you have any questions, happy to answer.
Thank you, Katia, for your nice presentation. Questions over there?
Thank you. My name is Mohamed Pila from Finger Automation. I have 2 questions. So if you could come back to the linear prototyping with JPEX slide, please.
Yep.
Can you comment on the activities surrounding packaging or assembly? This is the first question. And then the second question is which material platforms do you focus on at the moment?
Yes, excellent question. So in the packaging assembly, we have partners that can basically build, offer you packaging based on your design. Of course, it can be customized, but what we offer in JPEX is the concept of standard packaging. If you follow standard rules, then you know upfront how much the packaging will cost. Because yeah, the cost for packaging can be really crazy if you do not follow something that is compatible with the packaging process. So we want to make it clear and to provide these templates upfront to the users so that we limit, let's say, the number of errors and non-recurring engineering costs for the packaging. There are as well other options. For example, Fraunhofer HHI offers an assembly by themselves. This is something they developed for their own testing purposes, but now they offer to the service to their customers, where they can basically mount the chip on the assembly board. So there are different options which are good for maybe just characterization if you want to just understand whether your design is right, or you want to have it packaged to show to your investor. So there are multiple options. And of course, customization is always possible. Costs a lot, but we really strive, and all our partners offer the standard design rules. In terms of the platforms, we have 3-5, so it's indium phosphide platforms. We have silicon nitride, silicon insulator, and silicon photonics now offered by Cornerstone. They just joined recently JPEX.
Thank you. My final question would be, is there any guidelines, let's say, to download in terms of standard packaging schemes that you mentioned?
Guidelines,
yeah,
yes.
From
yes,
the website, I suppose?
Yes,
Okay.
yes. So basically, our packaging partners, they have the design manuals that both are there for the standard designs and for what their general capabilities for customized packaging is.
Thank you.
I have a question myself, Katya.
Yeah.
So, can you go back to the slide where you show all your, this one. How does an organization or company come to become part, actually, of the JPEX supply chain?
Yeah, it's a good question. Important part is that the company has to bring the added value to already existing ecosystem. The offer of this company has to be pre-priced, so it's really we're targeting the easy prototyping. So it has to be pre-priced, defined in terms of lead time, clear access conditions, and as well it has to integrate well, be interoperable with the offers of other players in the ecosystem. So, for example, if it's a foundry, then we ask the question whether they interested in, well, if they follow the same methodologies for data sharing, data validation, and standards that we use in JPEX, or if it's design software, whether they would like to, whether they can offer and build PDKs of our foundries using our methodologies. And the same whether if it's a packaging, for example, whether they can prove that they can package the chips from our foundries, whether there is a track record, and as well if they are ready to offer this standard entry-level product. So we really want to make PICs easy and make people believe and that the technology is as excited as we believe it is.
Okay, thank you. I would probably give a little bit more of detail to the question because I see many competitors in the different areas in your ecosystem. So, how is handling such kind of a family?
It's fun at times. I do not say that we are just happy family, but we do see that we can actually create more value by sharing. So, for example, like standardization and the data exchange, it's really the collaboration of many here. So even if one of one of our suppliers does an amazing job, they need to collaborate with the rest of the supply chain because for the customer, the end product is the sum of many. So therefore, we really want to work together with other partners, competitors, on developing the standards, the way how we exchange data, how we validate data, and to make it scalable, of course.
Okay, thank you. Is there any other question? No? So we will then thank you, Katya, again.
Thank you. Thank you.
And with this talk, we are closing the session on competence centers. I hope that you enjoyed it. Now, please, you can go enjoy a coffee break, and we will be back 11:30. Thank you.
Thank you very much to all of you for following the announcement of the next session. So this session is dedicated to end users and companies who are related to integrated photonics. And in order to do that, with the first talk that we have in this last session will be given by Peter van Anken from Photon Delta, who will give us an overview of the peaks in the Netherlands. So please, let's thanks Peter. Thank you very much.
So first of all, thank you very much for the invitation, for giving a speech here on demystifying PICs beyond datacom and AI. So I'm Peter van Arkel, I'm the CTO at Photon Delta. I've been trained as a physicist, worked a couple of years as R&D engineer in the electronics industry, and afterwards I started working as analyst and consultant at a consultancy agency where I specialized in integrated photonics and the technical side of things. So I did all kinds of analysis on the integrated photonics ecosystem, but I also did project management for complex R&D projects in the EU or in the Netherlands, and also set up a public-private partnership writing the technical content of the proposals. And hence I've been working in integrated photonics for a while now. And I want to talk today with you about, first a little bit about Photon Delta, the introduction of PICs beyond datacom and AI, followed by what are the actual barriers to adoption of integrated photonics beyond the datacom and AI markets that we all know pretty well by now, I think. And then a little bit about, okay, what would be the way forward? How can we do it together? And how can we follow up on this? So a little bit about Photon Delta. It is a new type of organization. I would say there's some organizational innovation going on. So starting with the Photon Delta ecosystem. The Photon Delta ecosystem is an end-to-end value chain, all the way from design to manufacturing, prototyping. You see there in the list of foundries, silicon nitride, you see indium phosphide, barium titanate, lithium niobate, aluminium oxide, very wide range of photonic platforms that can be used and can be integrated. Also with our packaging activities done by our partners, both photonic packaging, photonic electronic packaging and assembly. All the way up to the end users, the applications, people developing modules or products with integrated photonic. And we also have our partners in technology, supplying software, knowledge, and also equipment, because we also have a lot of equipment manufacturers aligned with our ecosystem. So this is an overview of all the activities within the Photon Delta ecosystem. So then there's the Photon Delta Foundation, the organization I work for, which has the same name, which sometimes is confusing with Photon Delta Foundation. We work with 28 people at this moment, or 28 FTE. And our goal is supporting an end-to-end value chain in photonics integration companies. We have a European outlook, and we are based in the Netherlands. So one of the activities is supply chain coordination, making sure that all the building blocks are there to have a successful end-to-end value chain. Also making sure there is enough funding available, that the market is developed and ready to adopt integrated photonics. Talent acquisition, if we want to grow as fast as we are saying that we'll be growing, we need a lot of talent. So we're actively involved in growing the pool of people who can work on the challenges, and also supporting R&D and technology to make this happen. Just to give a brief overview of what we're doing, because I think that what we are doing is the best overview to explain what we do, because there's no similar organization that I have found globally. So we have people working on program management. We have a 1.1 billion euro fund in a public-private partnership with the Dutch government, and we are the program manager. So we report to the government on the funding, and we also do the technology support there. So we do the program management. We also do technology road mapping, the worldwide roadmap on integrated photonics. The IPSI is also an initiative taken by Photon Delta and MIT together. And we also develop content for all the purposes of market development, supporting R&D, supply chain alignment. We have marketing activities and events. You can find us at a lot of trade shows as the Holland Pavilion or PIC Pavilion or Photon Delta Pavilion, whatever branding suits the organizations tagging along. And one of our main flagship events is PIC Summit Europe, which is held each year in the Netherlands. And last year we had about 700 participants from around the world talking about integrated photonics, where to go next, what's new. And we also organized the Photonics Innovation Day at Photonics West. We had a side event there and in the Silicon Valley, and about 400 people from the valley came there to learn more about integrated photonics, mainly from the big semiconductor industry. So I think we did a good job there in showing what integrated photonics can bring to the market. We're also represented at OC, PIC International, ECOC, Laser World of Photonics, Semicon, West, East, South, North. I'm not sure which wind directions there are, but we are usually there. We have a team working on human capital and talent acquisition. So one working with universities, educational institutes to align the education needs to the industry needs and the educational offerings, whether it's new programs or existing programs, changing the content. Also sometimes equipment, if you need to do practical education, we supply that. And we also do talent attraction, so branding integrated photonics is a very interesting dynamic field to work in. We have business developers represented all in the world to spread the gospel of integrated photonics and to get them adopted globally. We'd also do government relations from regional level to European level, and we have a startup fund to help with the first demonstrator. So this is a very brief, because I wanted to save a lot of time for also the content about demystifying PICs for different applications beyond Datacom and AI. So what we can, if you want to work with us, or if we want to work with you, I think it's always mutually beneficial. Things that we can provide is, for example, access to shared infrastructure that we have, joining trade shows, support in locating activities in the Netherlands, representing PICs in the Netherlands, in the EU, and globally, matchmaking with stakeholders. If you think you see interesting organizations in our ecosystem or want to get in contact, you can always reach out. That's also why my email address is plopped somewhere on the top of the screen. I made the slide specifically for this audience, otherwise it would have been a slick sheet with some general remarks, but I thought this might be interesting for this audience. Also the talent development, I think, might be something to work together on. Either joint training programs, design contests, workshops, student exchanges or student challenges. If this is interesting, drop me an email and I can connect you with the right people to talk further about this. And we also accept Photon Delta partners if they are strengthening the Photon Delta ecosystem, where we can also provide some of the activities that we do for you. I have to make clear the funding, the funding we got from the Dutch government needs to be spent in the Netherlands. But the activities we can do for a lot of organizations also outside of there. So we can do direct. I get this question a lot, so I spent a little bit of time explaining this, right? We are happy to work with everybody. I believe that we can only be a strong ecosystem if we all work together and show the industry that we're ready for their business. But this money stream is geo-fenced. Then a brief overview of the portfolio of companies. So there's the Photon Delta Startup Fund. The Photon Delta Startup Fund is tickets between 500K and 2 million to make a first demonstrator in integrated photonics. It's a loan, so the main goal is to have a first demonstrator in integrated photonics, to get the industry going, to learn about the market and to show the viability of integrated photonics. Photon Ventures is a commercial activity. In the past, Photon Delta has supported venture capital to companies, but we have spun this whole activity off to Photon Ventures, which is a completely separate organization, just to make sure, but we align on them on investments. So now the introduction to the different applications. So I'm very motivated to work on integrated photonics because it can really contribute to the big societal challenges we have. And I link this to some of the core sustainable development goals of the United Nations. For example, solving or helping to solve, we cannot do it alone, of course, with integrated photonics, helping to solve the challenges in zero hunger, be it by automating, for example, how you can harvest crops, or you can monitor whether they're ripe, or for measuring different environments for the plants or crops or animals to make sure it's most suitable for them to increase yields. We can work on better healthcare by making more affordable healthcare devices, or having them available in remote areas because of their size or handheld, and also better diagnostics for early detection. We can contribute to sustainable cities by making traffic more safe and more efficient. We can also help in infrastructure and science. There are a lot of scientific missions using integrated photonics for all kinds of measurements and communication. And climate action, which is mainly driven by datacom and AI. I always feel obliged to talk about datacom and AI because it's the biggest driver in integrated photonics, right? All the others are at this moment relatively small, or maybe non-existent, or in demonstrator phase, not the big volumes that we're knowing from there. And last year at PIC Summit Europe, I organized a program, and we had a full day dedicated to different application areas. And we had also big companies there like Airbus, Unilever, Sony talking about their needs of integrated photonics. And I got a lot of questions like, hey, I didn't know that integrated photonics was also used outside of datacom, or can be used, or that it's so mature that these big companies want to talk about their needs. And that got me thinking, what does the market report say? This is a public image from Yole, where they show their expectations. They published this in 2022 for the different markets. And you see here, for example, a very big blob about consumer health. 240 million euro on integrated photonic dies. That's a lot. That's a lot. And also you see there blobs for immunoassays, for automotive LiDAR, gyroscopes. So the future for integrated photonics looked very rosy outside of datacom. That's a remark you have to put after every sentence, I think, like that. And now we have the 2024 report again from their website, public image. You see datacom, 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 telecom, telecom, other. That was a little bit different story they have now. I can think of some market trends that I might have looked at, but I also think that I know a couple of companies that supply about twice the amount of other applications than predicted here, described here in 2023. And I'm not bashing them here at all. I have a background in consulting. I know how difficult it is to get data and then to do something that you can both fit your feeling about how the market goes and having the data for it, and you can never know everything. So that's not my main purpose of these slides. My main purpose is to say there's a lot of mystification going on in integrated photonics outside of datacom and AI. And I wanted to talk today about what we can do together as a community to figure out what's what. Right? There's so many different stories, so many different perspectives. And I took the barriers to adoption perspective. And let me be clear with you, I made a very nice, I hope very nice, I would like to have your feedback on it, framework on how to think about applications beyond datacom and AI. This is the first time I'm presenting it. I made it for you, and I hope you will appreciate this original content. It might not be a sleek slideshow like you're used for other pitches. The content in it you might challenge. Actually, that's the whole purpose of it. If you disagree, please tell me why. That will make us all learn, and I'll tell you why I put it there. And that way we can together come to a better understanding of what the end user needs from integrated photonics to start adopting the chips on volume. So this framework, the core of the framework is the CCR points. The cost point, the capability, and the reliability. And here the cost point is basically the price for a functional module that you need in your market to sell it to the consumer or the end user. I think this one is relatively straightforward. There's the capability. Not as straightforward, because for every application market, capability means something completely different. It could be power consumption, it could be the frequency, the scanning ranges, wavelengths, parallel markers, whatever is needed by the industry to say, okay, this is the function I need out of this module. And the final one is reliability. So reliability is also a very broad bucket that is not one easily defined thing. So it could be second sourcing. What's the reliability of your geopolitical division, or what if a fire breaks out, that type of reliability. It is the reliability of the known good die, or the yield that can be expected. It is about temperature and aging tests, that if you put it in your product that you don't have recalls every week. That would also be very nice for most customers, but then how often can you recall with new technologies? That type of questions are put in the bucket of reliability. So these are the CCR points. And one side note I make here is this is given the customer would actually place the order for a significant amount of volume that is expected with this market, right? If you just have one chip developed, you cannot get to the high reliability due to all the constraints in manufacturing. But this is a side note, okay? Given that we are mature enough, they will buy, we will develop the final parts, getting it up the TRL 8.9 scale. So that's the framework. The first question is the market actually ready? So if I want to adopt a chip, do I really need to change something? Well, that differs. For example, at this moment, we don't have wireless communication between a base station for 5G and between the fiber communication, for example. Not in a large volume. There probably are demonstrators, there are probably applications in smaller markets, but not on the telecom side. So that is a market that needs to change the way it works. And on the other hand, in LiDAR for engineering to check whether bridges are sustainable, that already exists. It's with discrete components. If you put a chip in the device, then they say, oh, nice, I have a cheaper, better component. I'll engineer it in and we can work with it. Everybody knows how this works. And then there's all kinds of grayscales. I mean, it's not a perfect framework. You can never get in detail, but I think it gives an image. And you might say, well, I know of applications that should be green. I think of applications that you are wrong, that it's right. That's perfectly fine. It's a first guesstimate I'm putting up here. So briefly going over the things that I expect you might have questions over what I mean. So I think LiDAR for automotive is kind of straightforward, right? Autonomous cars. For mobility, there I mean more the drones type of applications, warehousing, that type of activities. Agri-food for pruning, for example, or crop detection for harvesting. In engineering, I already gave the example, optical coherence tomography. For AI, AR, consumer, for example, the Google glasses, you already know about it, but also for mobility, you can have your windshield having all kinds of information on top of it. It's also artificial reality. And in industry, if you have engineers repairing equipment, for example, they can have a glass and get instructions right away, that type of applications. Process monitoring, like what is the content of the substance I'm working with, whether it's in agri-food, food processing, in healthcare, measuring different things about the blood or the skin or whatever. And then there's the consumer market, putting this in wearables like your watch. Biochips, market detection, whether you have some kind of sickness or disease. And in consumer lifestyle, a big example is glucose for in your watch. And then there are the fiber Bragg ratings for structural health monitoring of equipment. Gyroscopes, the mobility I see here as the civil sector, and then there's the defense sector, which is pulling a lot on these developments. Gas sensing for environmental sensing, for example, on nitrogen, CO2, methane gas, and all the others that are societally relevant. The optical wires communications. So there is Li-Fi from room to device. The metropolitan, where I mean somewhere between, well, connecting a room with a central point or a wireless station to a wired connection. But also, for example, between racks in data centers. There are all kinds of applications. I call them metropolitan. I'm not sure if it's the right name. Please, if you have a better suggestion for what I mean, let me know. For space, both in space and between space and ground, and beam shaping and beam steering in the wireless applications inside of base stations. And the final is communication and computation. Well, the transceivers are already there, so this one I know pretty sure. The only one I know pretty sure. And then there are switching, signal processing, and quantum applications, including quantum key distribution. This is a first estimation. And now I'm going to give you a little time to read it. I'm not going to try to read this whole slide to you. A first estimation of the cost point to enter the market. So here you see on the x-axis the estimated price for a module. I took this from my sleeve. I just thought like, okay, what do I think is reasonable for the automotive industry? I hope people will correct me on this. And that's on the x-axis, and on the y-axis I made 3 different lines. So I think that if you order the volume, we can get to that cost price that the industry needs. There is we are close, but we might need some developments in testing or better assembly, or it's significant developments are needed to get the technology to the point it can reach the cost price given the volume is there. So I'll give you 15 seconds to absorb all the different things. Write down what you don't like. I'll be here after during the lunch, and you can roast me for everything you would like to see different. And then I've done something similar for the capability. And each of the capabilities probably have a different reason why they are in a different bucket, and there might be competing ones. Again, there's no x-axis this time, because it's not a scale. But I sorted them per application area or per technology type. So the next one is on reliability. Again, same as the previous one, the 3 different categories and the 4 different technology lines. Feels like a questionnaire at school, right? You get a question, there's 15 seconds of silence, everybody starts scribbling down or taking pictures, and then you move on again. So based on this first sketch, I made this color disco that I also haven't made sense of yet. Again, you see all the different application areas and use cases, and all the color coding I applied to it as a first analysis in one overview. Yeah, maybe you can tell me what it means, but what I do see is there is a lot of green, there is a lot of orange. So the discussion that I hear like, oh, but it's almost there, or there are users already interested in adopting the technology, it's pretty close. I think that this first estimate aligns with that view for quite some applications. And on the other hand, there are also some significant roadblocks that might hamper the adoption. Although everything looks perfect, there's this one thing that might obstruct the adoption of the technology. And I think specifically in the reliability, there's something we need to do as an ecosystem as a whole. Getting the reliability of the supply chain sufficient for the big end users that they're willing to adopt, and not just the big players in this field that can deliver that type of reliability in their supply chain. And in my talking to a lot of users also, I found some other things that I could not put in these buckets. One of them is very human, I think. The lack of trust by the customer. Why should I adopt something new if I have something that works? Why would I take the gamble for something that's marginally better? Right? What's the wow factor that will get me, or maybe somebody in an organization with decision power who decides I'm going to take this risk? It's going to make or break my career, maybe even. And they usually need proof points, like somebody else who has done it before, which is a trustable, reputable organization. And another obstacle I hear frequently is also the need for functional modules. If organizations start shopping, specifically if they're not super big and have their whole R&D department who can do this, you can buy chips, you can buy packaging, you can buy assembly, you can buy designs, but you cannot buy the module you want. So you need to have experts in the field to orchestrate all these people. And there are a lot of efforts to align this, but I hear this often from the customer, and I think we need to direct them more to the people who know how to solve this together. And also the testing for reliability and environmental needs, where I see that they are asking like, okay, but if I put this in, will I get a recall every week? Okay, you've shown now that I trust every month, but will it be 10 years or will it be 1 year? And the customer often needs to be convinced. And these were the things that came to mind when I was doing this analysis, going through this thought experiment. I hope you enjoy going through this thought experiment with me. So that brings me to the conclusions based on the first thought experiment, right? So how conclusion is it actually? There are many markets that can adopt PICs, they are ready. And otherwise, the markets are ready for PICs, the market exists. But PIC technology is very close to meeting the requirements in many of these markets. But a reliable supply chain is a core bottleneck, or at least, let me rephrase this, maybe that's better. The image of a reliable supply chain by these users is something we can work on together, right? By being a reliable partner, by showing the industry that it can be done, by delivering proof points. And also the industry needs to start trusting the technology and make it a no-brainer, right? My competitor is doing it, so why won't I? That type of questions. That's the level where we should get. And this is also something we can do together, to work together as an ecosystem, to get these proof points, to convince the customer. And this is not this is a pre-competitive field in that sense, I believe, that we really can do something meaningful. So with that, I would like to conclude the brainstorm together with you. I'd be happy to be in contact with you afterwards. I'll be here also during the lunch break where you can grill me on everything that I've said. You can also meet me at PIC International. I think it's in 3 weeks. I'd be happy to further discuss there if you are also there. And also an invitation to PIC Summit Europe, 4th and 5th of November. Or drop me an email. I'd be happy to talk further and hopefully also learn from your insights. Thank you.
Thank you very much, Peter. Any questions or comments?
Sorry, yeah, Alexander, company Nanoscribe. And just one question. So obviously we are in Europe, not in the US, but you just gave an overview about our markets already ready. And I mean, in the US, I would probably see more often military and defense. So would that not to be included more often than you just, I mean, you mentioned it once for gyroscopy and defense, but I think probably it would appear in other countries more often than
yes.
here. Not sure if I would like that, but yeah.
I think you addressed very well brainstorm I had with myself in advance also. Where to put it, you want to consolidate as much as possible, and then I have this definition of volume where you can kind of fill parts of a pure PIC foundry, so not the huge silicon photonics guys who say, okay, I also want to put now in the silicon infrastructure also some integrated photonics and everything I see is small, right, the tens of thousands of wafer types. And I do see a big driver, and I think here in Europe since 2 days, I saw somebody, I'm not sure if it was a meme or real, I still need to check the shares of Rheinmetall going through the roof times 3 or something like that. I'm not sure if somebody's now smiling very happily. But you are right, yes, defense can be a very big driver. What I am still unfamiliar with is what can we expect, given that the supply chains are usually also quite fragmented between who is making the equipment, right, who's making the the plane or who's making the car or whatever, and where they source their technology from. So how big will then the market be, whether it would fit in here or not. But I think it can be a very good driver to really push this technology to the proof points I was talking about. Yes.
We have another question over there.
Thank you so much. I mean, it's a great summary. I think one, in my opinion, one dimensions I think you should also take a look into it is the also existence of competing technologies. I think, in my opinion, that is probably one of the other reasons that plague integrated photonics more than anything else, not just the technology or supply chain is available. For example, let's take a case of your biochips, right? Which you say that, I mean, they are going against technology which is just piece of paper, right? It's like, I'm talking about a COVID test. I mean, it's really hard. That's like fraction of a sense when they do it and then you throw it away. Or like QKD is going against the technology of like the normal cryptography, which is incredibly successful technology. So I think that's kind of, to give a, let's say, holistic picture, you have to put this into account that if you're just making like 10% improvement into something which is incredibly reliable, it becomes incredibly difficult to actually adopt.
Yes, I fully agree on that point. It is kind of embedded in this slide already, right? If it's green, it means there is a competing technology already successful in addressing the market. If it's red, I don't see a direct competitor in a similar field. And it also trickles down to all the different estimations, like, okay, can we get the right cost point? Sometimes the cost point is just compared to the competitor, right? Competing technology. Sometimes the capability is okay, but if I use electronics or if I use whatever technology, it will be 3 times better than what integrated photonics can deliver. So you're right, yes. And it's good to take into account when putting these applications on the slide and trying to judge where they fall, to keep this into account. Thank you.
Thank you. One last question.
Yeah, thanks, Peter. That was a great summary. I just have a question regarding your metric of like market readiness, because I think on one of the slides you had a kind of a measure like where it was green, while the cost and the reliability were red. So I'm just wondering, like, maybe I didn't follow properly, but like how, like OWC Li-Fi, for example, right, is market ready, but everything else is red. I'm just wondering, like, in that definition, how is it market ready?
Yes, so the definition of is the market ready is there a does the market have something similar that can be replaced by integrated photonics? And here I marked the market is ready, green, because we all know Wi-Fi, right? If I go into a room and I connect to my phone, then oh, I have internet. If you would replace this with Li-Fi, the lights are on and I walk in my room, the user will not see any different change. So the market might need to change the technology they put in, but the user and the market doesn't really need to change in a big way, which would be different in the automotive industry, right? If we're all driving in autonomous cars, that would mean a whole shift in the economy. It would mean a whole shift in the laws we need. And that's kind of the differentiation I try to make with the metric market readiness.
Okay. Okay, thank you very much.
And please don't quote me on this like Photon Delta says this is the truth. Please make sure if you show this to anyone to say, otherwise I'll be hanging somewhere, I guess. Thank you.
Thank you.
Okay, so now we can move on to the next speaker, who is Sebastián Echeverría from Lux Quanta. So please, Sebastián.
Okay, hello everyone. Yes, my name is Sebastián Echeverría. I'm the CTO of Lux Quanta. First of all, thank you for the invitation to give this presentation here. The title of this talk is Quantum Key Distribution System from Discrete Assemblies to peaks. So this was a suggestion from Pascual, which I think is very nice because this is actually what is happening in QKD, that we are reaching some maturity in products made with discrete components, and we are working on R&D for the next step that will be photonic integration. So I move here. So just a bit about Lux Quanta technology. So we are a spin-off from ICFO in Barcelona. So we were founded in May 2021. Currently, we are 32 employees. And actually, when I was preparing this presentation, I found old slide that I gave here 2 years ago, which it had a similar picture, but there were like 6 people there, which is very nice to see like how things have evolved for us. We are growing now, and a lot on the technical side, but as well on the commercial, because we start seeing some market traction and some like a lot of proof of concept happening in QKD at this moment. We are focused on a particular variant of QKD that is called continuous variable QKD that I will talk a bit later. And we have had well, investment from companies, one in corporate venture capital, one from Barcelona area on software, and also Corning, that is the optical fiber and glass manufacturer from the US. So, well, I think that most of you here are familiar with QKD. I heard that those words many times today. But just as a brief of introduction on QKD, so this is the main motivation of working on QKD or having QKD projects is because of the threat that quantum computing is posing on the way that we secure transmission of data today. So we are based on mathematical cryptography, asymmetric cryptography, which we rely on some one-way mathematical functions that we believe that are secure with classical or standard computer that cannot be reversed. Main example, and it is also the base of the main cryptography algorithm, is the factorization of large numbers, which you cannot do efficiently with a classical computer. So that is the basis of the RSA algorithm that we use for digital signatures and also for establishing secret keys between two locations. So that algorithm particularly, or also some other algorithms that are used today, are expected to be, well, when there is a large enough quantum computer and they can run a specific algorithm that already has been proposed, they could solve those problems efficiently. So this is something that is expected to happen. We don't know yet when. Also, when I prepared this presentation 2 years ago, I had a slide saying that the quantum computer would be available in 15 years. I removed that because actually I was not going to put 13 years because I think people still think 15, 20 years. So we don't know. We don't know when the quantum computer will be available, but we do know that there is a lot of investment going on that. So it was 50 billion last year. There is Google, IBM, Microsoft recently also got some milestones. Amazon is a new player on this, and also a lot of startups and, well, not a startup, like companies that are not these ones, but actually have become quite big, doing different platforms for quantum computer, like superconducting circuits, ions, etc. So there is a lot of investment, and we will tend to think that this investment will give, at some point, a quantum computer. It happens, well, 10 years, 20 years, doesn't really matter so much, well, because this is a problem that is affecting us now in the sense of also threat and also the fact that data can be stored and then decrypted later. So there is a time that the data should be secure. So if that is 20 years, depending on the type of data, that can be vulnerable today. And since it's cybersecurity also, we cannot really take a risk saying, okay, maybe nothing happened with the quantum computer. So it's a good opportunity also to, considering that the QKD technology is mature, to actually improve the cybersecurity once for all. And that is why I have this graph here. So quantum QKD, differently than mathematical cryptography, the foundation is on quantum physics. So it's information security, information theoretic security. So the assumption is not based on any computational capability of an adversary. It's only based on physics, quantum physics principle. So RSA is based on mathematical problems that are associated to a computational capacity of an adversary. RSA, we know that there is an algorithm that can run in a quantum computer that can break it. So then there is an alternative to this, is that to come up with different mathematical algorithms that we don't know yet how a quantum computer can break. That area of work is called post-quantum cryptography. It's still mathematics-based, but it's a different algorithm, not factorization of prime numbers, but lattices, error correction codes, etc. So, and this graph shows more or less how it's seen the evolution of the technologies as a function of time and the possibility of an encryption algorithm is broken. So you can see there that where is the orange is RSA. It's basically like from the past, from the 60s. is evolving in this way because a given number of years we need to increase the size of the key because we become better at doing computation. So it goes like this. But there is a moment that there is a quantum computer that RSA basically is broken because it's already not the way that it scales with a quantum computer is not exponential with the length of the key, but it's polynomic, so then it doesn't work, this type of increasing the size of the key to solve the issue. And then we have PQC, that it continues the same way that we have been in the past. So basically, it will be a mathematical solution that will be patched every certain number of years once the technology, the computational capability becomes better. PQC has also some other problems as well that is we need to prove it against quantum computer, but also against classical computer, because it's new mathematics. So QKD, it comes with a lot of challenges to install QKD technology. But then the idea is that the security of that stays constant over time, because it's not based on any computational assumption of any adversary. So that actually motivates the investment in QKD, but still, as it was said, it's a technology that is complex compared to just using mathematics and software. Or rather than complex, it's different to what we are used to in cybersecurity. So that actually poses some challenges that we are trying to address as a company, well, also the whole ecosystem. So I go briefly on this because I think most of you know about QKD, but it's a telecommunication system. You have a transmitter and a receiver. This is in the most basic or like most mature way of having a QKD technology. So you prepare, with a transmitter, you prepare quantum states, which is light with some encoded information. You transmit it into an optical channel that typically would be an optical fiber when we are talking about terrestrial networks. And then on the other side, you have a receiver module that can measure the information that is encoded in those photons. And then doing this communication between a transmitter and a receiver, plus some data post-processing, we can distill cryptographic keys on both locations. The keys are completely symmetric, so they are identical and they are truly random. So there is no mathematics to create. They come from a quantum random number generator as well. So then, and after that, after you generate the keys, everything is as usual, nothing changes. You can have whatever we use today, VPN, IPsec, encryptors, so they get the keys. Instead of those modules negotiating the keys with RSA, they would use the QKD. So the main security advantage of this is that when an intruder will tamper with the quantum channel, with this quantum signal, when performing a measurement to that to gain some information, we'll add noise. That is part of quantum physics property. So that noise will reveal the presence. And basically, the trusted parties, the transmitter and the receiver, will know that there was someone in the channel, so the keys will not be used. Okay, so just some example of what has been happening. Well, this is from a report of 2019, but it gives a good idea of what was happening at the time. This has evolved a lot recently, but there had been QKD networks being set up for many, many years. Some of them are more like pilot or like pre-production, but still they have reached some scale. For instance, the one in Madrid, it's, I think, more than 40 nodes that has been the effort of particularly Telefonica with the UPM and other companies there on growing this. It's very nice because they have telecommunication network where the QKD, it's integrated in a way that is not an ad hoc QKD network. It's more like a standard telco network that is trying to integrate QKD. So they have worked a lot on standardization of interfaces and also co-propagation, classical quantum in the same optical fibers. There is a larger network in China. I think it was 2,000 kilometers of links covered by QKD, and also they have the satellite that was launched in 2015, and now they are launching 2 more, or they did launch 1 more, I think, and they're launching another one. So this is kind of the largest QKD network in the world. There has been also some work done in South Korea, Italy, the UK, that to some extent they have deployed QKD networks, but also trying to do kind of commercial, particularly the one in the UK, commercial kind of pilots, so try to involve end users like banks, government offices. Well, also in the Telefonica one. But this was 2019. Then, then in 2021, so this is kind of first, let's say, a big pilot phase. But in 2021, there was a signed agreement, and we started a series of European projects on deploying a large-scale QKD network in Europe to secure digital critical infrastructure. That started by some projects on national deployments, so basically giving funds to consortium from all the member states to start buying QKD technology. Also, there were calls for manufacturers to mature their technology to high TRL and also to include the security part. You know, this technology comes from photonics and physics, and we are evolving towards a cybersecurity product, so there is a lot to be considered there. But this was a really good push for us because we started selling systems to many countries. Each member state started deploying metropolitan networks. Now they are trying to, or they will start to do the cross-border links. So it's been a good opportunity for all the QKD manufacturers to start putting the technology into the field and to work with end user and also with telco operators into identifying the missing aspect of the technology and how to improve them. And that's why there were some also projects that are industrial for companies like us to increase the technology maturity. And then we have this project Quarter that is one of them, one of those projects. So this actually is a 10 years project, and by 2032, expect there is the kind of this idea of having this large-scale QKD network in Europe. That is also a joint project. There are joint projects with the ESA to have also satellite links. Okay, so now we go more into technical parts of the QKD and then on the photonic integration. So then I said before that we do CVQKD or continuous variable. Differences are mainly on the detection technology. So discrete variable, or like the same more standard QKD, you prepare those photons, you encode some random numbers in any degree of freedom of the photons with some particular conditions, but could be polarization, for instance, for polarization state of the photon, or also phase and time. But then you have this photon source, and then you have an SPD with some interferometer to measure the information encoded in the photon, but the main detection happens with an SPD. So this is, let's say, the first QKD technology that reached commercial maturity. So this technology is it's commercial for many, many years and has some advantages that can operate at long distances. So you can have the transmitter and the receiver separated for more than 120 kilometers with standard equipment. But also if you use superconducting nanowires, you can extend that to 300 kilometers. And also it can be good for satellite links. So it's the one that has been used by China and is being used by the European projects on satellite links. So continuous variable QKD, it's, as it says, a coherent detector. So instead of having an SPD, on the receiver you have a second laser source, which is a local oscillator that is mixed with the signals, and they are amplified, and then you can use normal photodiodes. You don't need SPDs. In this case, the modulation has to be in the phase and the amplitude, or in the quadratures of the electromagnetic field, which is what is used in telecommunication when you use I and Q modulation. So it has some advantages because it's based on standard components, standard photodiodes, and one particular advantage is that this type of detection is very narrow bandwidth, so it's very resistant to background light. So basically you can use the same optical fiber with the QKD, but also you can put data channels there. You don't need to install a new optical fiber in most of the cases. And then, the performance at short, medium distance of less than 100 kilometers, it's really good. So these are the two main QKD technologies, but there are other more based on entanglement or different type of configurations that would fit into discrete variables, but not in the type prepare and measurement like this. But I just focus on these two. So just because now it will try to go into photonic integration, I'm covering a bit the photonic layer of a CVQKD technology. So typically you will have a laser source, then you will have a modulation unit. So We typically would use amplitude and phase modulators, or you can use directly IQ modulation. Both would work the same. Then you need some monitoring, tapping detectors, or some technology that would allow you to have a very stable system, you know, like the modulators are always operating at the right point because you need really high levels of stability. And then you have an optical attenuator that will bring this to the photon level. So in the end, you need to send single photons. Then you have also power meter because you need to know exactly the number of photons that are output in your transmitter. All of those parameters are needed, and they all need to be really stable over time because you need to measure really low levels of noise. In this particular protocol of continuous variable, we use Gaussian modulation. So that is just kind of a protocol detail that in telecommunication you would use like more like QPSK or like constellations that are 64 values. We have to use Gaussian, like with this profile, and with high resolution, like several values. And then you propagate those quantum states to a receiver. So the receiver, as I said, has a local oscillator that is combined with the quantum signal by using, in this implementation that is standard, an optical hybrid to recover the I and Q quadrators, and then with photodetectors. There are other possible ways. You can use a heterodyne type of detection. So everything that we do in telecommunication applies here. So, but this is kind of a homodyne type of detection. And then you have FPGAs to control everything, and for DSP, and you need to do a lot of digital signal processing, including clock recovery, frequency estimation, phase recovery. And then you have some software that needs to run the data processing that I mentioned before. That is error correction, and basically obtain the secret keys. So then the challenge of this is that we need to really keep all the noises of the system extremely low. So this detection has to be shot noise limited, but all the practical noise of the system, for instance, we are having values that are 0.1 milli-shot noise units. So these are the practical noise. So that includes all the sources of noise, from laser line width, like phase noise from the laser, crosstalk from modulators, quantization, any type of source of noise we need to try to minimize, because the higher this excess noise or practical noise, the less performance we will have. Because as I said, the intruder will modify the quantum states and will increase this noise. But there is a threshold where the keys will be kind of zero. So in that sense, we need to keep the practical noise as low as possible. And this is most of our know-how comes to how to actually minimize this noise to have a 100-kilometer distance, for instance, instead of 10 kilometers. And well, talking a bit of marketing here. So this technology, well, we launched the first product in the beginning of 2023, yes, 23. And now we're having a second generation. We have kind of made some changes in hardware and also in performance, so we decided to change a bit also the box and the form factor. And this moment is being announced or promoted in the Mobile World Congress in Barcelona, which with this CVQKD technology, we can reach 100 kilometers. The first product was launched with 40 kilometers only, and we really characterize the propagation of quantum signals in optical fibers that are lit, are with data channels, and also in some cases with amplified data, not like the data channels, not the quantum signal, but the data went through an amplification by using EDFA that is common in telecommunication. So how the noise from the EDFA would affect the QKDs, and how you need actually to filter that noise to be able to co-propagate. So that was a study that we did, so we could put some numbers to the capabilities of our QKD to be installed in existing infrastructure. So I might be too late with time because I will try to speed up a bit. So, because actually that was all the introduction, but this is what well, I will try to be brief on this, but the title of this talk was From Discrete System to Peak. So I tried to put some interesting development that happened from 2019. For instance, the first integration, this is particularly focused to CVQKD, that is what we do. There has been also some work on DVQKD, always not integrating the SPDs, but there has been some level of integration with DVQKD technology. But particularly in CVQKD, in 2019, there was a work that they integrate a lot of components except of the laser, And they use a scheme that is a bit obsolete, that the local oscillator is transmitter from the transmitter to the receiver, but it was a good first, let's say, integration in silicon photonic. Then 2021, there was a nice work from ICMEC on a detector that operates a really high bandwidth for and is shot noise limited with a good clearance, so you have shot noise 10 or 20 dB above the electronic noise, that this is what we need. Then in 2022, this was a work that we did with ICFO, that was part of a project called CIVIC from the Quantum Flagship at the time. Also VLC Photonic was involved on that, and HHI, and this was an indium phosphide transmitter. Also not including the laser, but was the first transmitter in indium phosphide for CVQKD. Then in 2023, there were some works on receivers. So basically, the receiver that was done by IMEC before was used for a QKD system that they reached really high speed. And then there was another receiver done in silicon photonics. So this has been the main papers that I could pinpoint on integrated CVQKD. I will focus a bit more on this one, on the indium phosphide, because it's the one that we were working on. So this is basically an IQ modulator. So the laser is an external component in here. And this was part of the CIVIC project, was designed together with VLC Photonic and other partners and manufactured by HHI. And after some iterations, we got some chips that were functional and that we could perform some measurement and some characterization. So then for characterizing, of course, we needed to have a receiver, and then we use an experimental setup where part of the components also were outside. But the interesting thing of this, that this was a paper that was published some months ago in Optic Express, that I should have the reference here, but it's not. But then we could actually obtain secret key rate with this chip. And well, even though the performance still needs to be improved, it was the first time that indium phosphide was used in this CVQKD technology. Of course, there are some still improvements to do, like trying to integrate the laser and also working on the receiver side. And now, well, this is kind of happening now. So there is this framework partnership agreement, QTest and QPilot, where we are an end user. And we have been working with HHI to continue this work on the transmitter, where the next step, of course, would be integrating the laser together with this encoder. Let's say encoder would be the IQ modulator. So we are exploring the co-packaging, so we exchange requirements, and then it's very interesting, this design, because also the isolator is included there as this polyboard platform that they have. And this is an ongoing process, so this is, they have obtained some result, but this is an ongoing project. There is also for the receiver, within also QTest and QPilot, there is the work with VTT, where they are using their thick 3 micrometer platform to do the integrated detectors, their germanium, and also with integrating the TIA. And also they published a paper on this, and it has been, well, we have been getting some results, like for instance, the common mode rejection rate is important for us, as I mentioned, to mitigate any source of noise. So then they have reached 30 dB with this. Also, the responsivity of the detector is very important for the detection efficiency. And just to conclude a bit on the challenges on this, which is kind of always the input that we provide to companies working on photonic integration design or also foundries, on what are our needs. Of course, our needs are always evolving because depend on our typical or particular implementation of the technology. So for instance, the main challenge of all of this is the laser. I think it's always the case in photonic integrated components, but for us, we need narrow linewidth for keeping the phase noise low. We need high frequency stability, so we need to lock for coherent detection, we need two lasers to be interfering with each other so they cannot drift apart, either by having some active stabilization or being really referenced to something, some external reference, but we need the laser to be interfering. That could be within 200 megahertz, for instance, that is our detection bandwidth. Ideally, we want, well, ideally I put, because it's maybe asking too much, we want this laser to be tunable in the whole C-band, because our customer would like to put the quantum channel wherever they want in the fiber. So I will jump to that the last point that is very important, no side effect of uncontrolled behavior, which it's really important because in the end, this QKD technology combines telecommunication with photonic integration and quantum, but it's a security technology. So it's very important that there are no side information. It's extremely important that when we modulate the phase of the laser, the phase of the amplitude is not doing anything else, or that there are no mode hops in the laser that goes to an unknown behavior of the laser. So that actually has been a problem for us even with commercial lasers, like mature technology. So that is also important to be considered. That is for the laser. For the modulators, we need high extinction as well because we do some digital signal processing that we need to put some pilot symbols that have much higher amplitude than the quantum signal for all the clock recovery. So that puts some requirements on the extinction of the modulators. And the detector has to be shot noise limited. That is more like under control, I think, with more requirements on the electronics. The low loss receiver, well, yeah, the more the losses, the less performance we have. So ideally, we want to have also low losses. And this is more or less considering what we have now, but it could be interesting also polarization management because we can add some capabilities to our receiver, for instance, to measure both polarization. Instead of doing an active tracking of polarization, we can do diversity if we have a PBS, and we benefit for photonic integration that can be done cheaper than actually replicating the optical hybrids and the detectors. Yeah, thank you very much. And for anything, there is my email.
Thank you. Thank you, Sebastian. I don't know if there is any question, but I think we should move on. If there are any questions, you will stay for lunch, right? Yes. Okay, so you can reach Sebastian during the lunch time. Thank you, thank you very much.
And the third talk of this session is given by Gernot Hamann from Physics Instrument.
So, hello. Now comes the first challenge, even before I try to operate this one here. How do I address you? Do I say good morning or do I say good afternoon? So Germans would say good morning, good afternoon now, but I think for you it's still morning, so I try it different. Buenos dias. Okay, let's get started. So this is not the first slide. I will be there in just a second. So, okay. Okay. So let's get started. It's microns to mode fields, so you can already guess it has something to do with accuracy and positioning. That's also what our company stands for, and how this is used to advance automation in silicon photonics and also in integrated photonics. So if you look at this picture, you actually see a lightning, and at the end of the presentation, you will know which reference this lightning has to the talk. That's what I can promise. So let's start. First, a few words, but I will make this very short, about our company, about PI. PI is a global company located, the headquarters are located in Germany, in Karlsruhe. That's also where I'm coming from. It's privately owned. It was founded in the 1970s, so it's pretty old already. By now we have 1,700 employees, even more. So this year we might get very close to 2,000 actually worldwide. One of the characteristics of PI is that we have our core technologies developed in-house. This makes us very flexible in reacting to customer needs. And we, from the beginning, basically our main objective was to get good connections to both the education to the universities and also to the industry and partner with them and being always at the forefront of technology. So we have a lot of OEMs, for example, that we are working together with since more than 20 years. So long-standing customer relations are very important for us. If we look at our global structure, then you see that we are globally represented in the Americas, in Europe, in Germany, for sure, but also in Asia. We have quite some presence, both with sales offices, but also with design and production centers. So we are developing to be a real global company. Now, let's switch to the topic that's probably more interesting to you. So the PICs, Foundation for Data and Communication Technology. And I'm a bit ashamed now because Peter has given such an excellent talk about all the business aspects, and I just have one slide, which I might have removed actually if I had known that you were going on this in greater detail. But actually, why are we interested, or why do we see this as a big business opportunity for us? So what we see and what we heard is, again, it's artificial intelligence in data centers, right? No surprise. And the incredible need for power that really in some cases makes them problems, right? It's really generating problems because, for example, Google was denied a data center in Dublin because it would have consumed too much energy and the infrastructure couldn't take it. That's not the only thing. Microsoft in the US, they are thinking about repowering 3 Mile Island. Now, I'm old enough to remember 3 Mile Island, and I think it must give some guys the creeps if they see this repowered. But anyhow, that's how big the need for energy of these large data centers is. And that's a very strong point in driving integrated circuits, because with this you can actually decrease the power consumption of these data centers drastically. So, going to the key advantages, I don't need to tell so much because you know this better than I do. Energy efficiency, high-speed data transmission, we heard about that already. Lower latency, increased bandwidth, and how PICs work. Okay, telling you this would be, like we say in Germany, carrying oils to Athens. Yeah, so I don't need to do that. It's just transceivers, basically interconnects and optical modulators. These are the elements that we are mostly talking about here. Now, key steps in the journey of a product from design to mass production. Well, we also saw this in great detail, so I don't want to go too much into detail here, just highlighting 2 of those areas. It's test and characterization, and it's also final testing and quality assurance. This is where you definitely will need to do testing, and for this testing, you typically need alignment engines that will actually align your integrated fiber chips or parts of your integrated fiber chips to the external world. Also, the packaging might be interesting here. We have seen some applications in optical packaging already where customers were approaching us. Honestly, it was not for integrated circuits, but I also think that the packaging process itself will also need help from alignment. Yeah, now to the main topic of the talk. Advancing automation in PIC testing. First, I want to say I'm going to split this into 2 parts. The first part that I will touch now will be about precision and positioning technology. The second, so it will be about the precision part. The second part will then be about speed, because precision and speed are both important for the automation task. Why is alignment critical? I mean, to be honest, we as a company, we are really happy that alignment is critical and requiring good precision, because this is partially what we are making our living out of. Yeah? But the basic fact is that optical structures are much smaller than conventional electronics interconnects. So this means that also when you try to align them, you need higher precision levels. For photonics integrated circuits, you need checking at different levels in order to make sure that they are working. And in order to do so, you need to align typically an optical probe together with your chip that you are testing, or with the part of the chip that you are testing. In a lot of cases, this will need multi-axis alignment because you will need to align both linear and also angular axes. You will have to do so with a high precision level, as the structures that you are aligning, or let's say better, the mode fields that you are aligning, are of very small dimensions, and you need to align them to fractions of their size. So you have different, is this a laser? No, yeah? No, it's not, doesn't mind. So I think that was too fast. So you have different ways to do that. Sometimes you only have to feed light in, then you have a one-sided design. Sometimes you need to look at incoming light, so you need to feed it into your circuit, and you need to, at the same time, look at another place at the outcoming light. Then you have two-sided alignment. Both we can help you with. For both, we have mechanics, which allow you to have 6 degrees of freedom and have a very high precision. What we have here is actually, let's see what this, yeah. If you look at it closely, you actually see that you have here something we call a hexapod, a 6-axis positioning system, and on top of this, you have another small device which is piezo-driven. So you have a combination of a quotation mark coarse, but already very accurate hexapod together with a piezo system that really brings you down to the nanometer range in motion that you can achieve. And you can have this single or double-sided. We'll talk about the alignment routines that go with this in a minute. This is just now, for the moment, let's focus on the mechanical parts. The main tasks that need to be done is to get light out of the chip and to couple light into the chip. Methods used to do this are, first, you can do surface coupling, right? So you have specific gratings that actually couple the light out of your wave conduction channels inside the wafer. Or the second one is you have edge coupling. Now, if you have surface coupling, that's easier to test. It's easy accessible. But the thing is, you're actually diverting light out of the plane where you really want to work with it. That's not so good. So typically you have to cut away some parts after the testing because you actually don't want this to happen in the package state. The edge coupling is more difficult to do, especially if you have to do it on wafer level. Then you have to cut special trenches where you have to get into and actually get the light out. Now both are actually requiring high precision, but especially the edge coupling, as we learned yesterday, the whole beam, the whole width of the mode field is something like 200 or 300 nanometers. And as you want to precisely position your probe in this, it needs to be significantly better than that. And that's how you get to the requirement that you need nanometer resolution and precision in the positioning. I just have this here as a picture. So when you're looking, for example, that you now have to match a fiber that is bringing the light or taking the light out to the cross section of the silicon waveguide and also of the mode field, you typically need to do this with tapered, I think it's a correct expression, right? Tapered fibers in order to adapt those mode fields to each other. Otherwise, you would just lose too much light and the coupling intensity would be too bad. But this again means that you have to be in the order of accuracy of much better than 200 or 300 nanometers in your positioning. A few of our products, the mechanical parts that are used for this, I already explained to you the basic setup. It's a hexapod with a we call it nanocube, with a piezo element on top. We can talk about specs if you're interested later. I don't want to go into too much detail, otherwise time will not be enough. But we have this as 1- and 2-sided versions, and they are accurate enough for all of the jobs that I've described before. We also have stacked systems, so we not only have hexapods as basis, but also stacked systems consisting of individual stages. And we just released another product that doesn't have the piezo part with it, but also comes with advanced control and also can run our alignment routines. So important part of everything for sure is the controls. We also do the controls ourselves or have it in our company group, so we can optimize this performance for the tasks that we have here. And for sure, when we are measuring, we also measure the quantities that you are interested in, not only positioning, but also the time it takes to align, the coupling efficiency that can be achieved in specific coupling cases, use cases, as well as the coupling stability and the coupling repeatability, because this, in the last account, is what counts in your applications. Yeah, so we've talked a bit about the mechanical side of business. Now let's talk about the algorithms that we have and how we increase the throughput with this, because the precision, on one hand, of the testing is very important, that you have an idea how reliable your parts are, and also for knowing the true actually performance that you can achieve. But the other thing that is very important is we are talking here about your ability to develop this process into mass production, and then time is of the essence, and cost. And the cost to test and align has been traditionally quite high, as long as things were not standardized and not well fitting to each other. But we have developed a set of algorithms that helps you to decrease this time greatly. So what you are seeing here is not super special. You are seeing 2 area scans. Yeah? You see a peak, an intensity peak, a typical mode field, and you see 2 ways of doing area scans to find first light. After you found first light, what you want to do is to go to the maximum. That's typically the job for alignment. And then what you do is a gradient search. So you walk along the hill and always go upwards until you reach the maximum. This has been around for quite some time, but also here our algorithms are very reliable and fast. But we added some layer on top. We can do more than 1 axis in parallel. So for example, a typical task in photonics is that you have to align a fiber band, fiber array, to, let's say, its counterpart on the other side. So what you need to do, you need to move in the XY plane until one of the edges of the fiber band matches the edge of the other. And then you have to do a rotary motion, in order to bring the 2 into that they are totally parallel. In order to do this, you have typically to do it at least 1 time. But then when you are doing the angular motion, you shift the lateral a little bit. Even if you have pivot point anywhere like we have, so you can define the pivot point you want to turn around, you still get some unwanted crosstalk, and that will deteriorate the coupling intensity. So typically you have to do this in an iterative process, repeat it, repeat it, repeat it, but we can do it in parallel. So at the same time, you are doing the XY alignment, you also do this rotary alignment. And the trick is you can do this with one optical signal, and we can break the components down and align on these components. So that's a pretty neat trick that really helps you to decrease alignment time a lot, and that's actually present in the systems that I just showed you. So, next one. But as we have seen, the alignment was only one part, right? We also have the first light. Now, finding first light can be an easy task. It can also be a very hard task, even if you know approximately where it should be. If you have a one-sided setup where you only have input, it's not so hard to find first light. But especially if you have setups where you have input and output, so double-sided, then finding first light can be tedious, take a long time. And that's where our new algorithm really helps. It's not doing a continuous motion. There are some tricks to it, yeah. And we actually can find the first light much quicker than with traditional scanning area algorithms. So, for example, the real beauty, for example, comes into play when you are using a double-sided one for production purposes. So you know approximately where you are, you don't have to travel that far, and by doing this, you really end up in double-sided first light find in less than a second. And also the alignment afterwards is very quick. Good. I think I finished pretty much in time. So I would just like to show you one thing. We are also working on stacked approaches. That's from our US colleagues. You might have seen this on the Photonics West if you were there. So it was on display there. So we are also working not only on the hexapod nanocube combination, but we are also working on new combinations of stacked axes, including rotary. Okay, that's all from my side.
Thank you very much, Gernot. I think we have time for one fast question. If not, you know that Gernot and Thomas have a booth downstairs, so you can also visit them and ask them more about their equipment and their capabilities. So okay. Thank you very much, Gernot. Thank you. Thank you. Let's finish.
And now we move to the last talk of this session, who is given by Joaquín Matres from GDS Factory.
Testing. Oh yeah, perfect. Hi. How many of you have heard of GDS Factory before? Just raise your hand. Okay, nice. Perfect. Yeah. Okay, so I'm Joaquin. I'm one of the creators of GDS Factory, and today I'm going to be showing you like the capabilities of the software and how it has evolved over the last 6 years. So we are basically a team of industry veterans, and we've been in many different companies where we have helped the companies adopt GDS Factory. But in the process of adopting GDS Factory, we also realized there were many needs that were not covered by this open source software. So for those who don't know, like GDS Factory is an open source library that makes chip design easy to use and very fast. If you don't know about the software, it's been downloaded over 2 million times, and it has over like 79 developers worldwide. And just to give you an idea of how many downloads we're getting, it's like in the order of 500K in the last 5 months. How does it compare with other software? Like I'm a chip designer, and I've been making chips for 15 years. I actually have tried every single tool before we decided to make GDS Factory. Like to give you an idea, I was in a company building like very complex like quantum circuits. It was taking us 2 hours to make a chip, just to render the GDS. we switched to GDS Factory and we cut down to seconds. How is that possible? It's because we use a very powerful library called klayout. It's based on C++. So it's like going from pure Python implementation or other languages into like C++, even though we have a Python library to control it. Another thing we also notice is that a lot of people are not doing schematic capture. Like when you're doing circuits in electronics, you usually start with schematics. Schematics is the map of what you're going to build. In photonics, a lot of people just do layout. The problem if you only do layout is that you don't have anything to compare your reference design with the implementation. So the layout will be the implementations, the layout will, the schematic will be the map. So you have to make sure you build what actually you intended to build. And this is very important when you do like very complex circuits. Another thing which was very hard to do is like device level simulation, circuit level simulation. So we basically built that into GDS Factory Plus. It's shown here on the right. So if another thing we have to do as an open source project, it was very hard to maintain Foundry PDKs, especially because all these Foundry PDKs are, 6 of them are open access, so you can download them for free. But the other 19 are basically, you need to sign an NDA with the Foundry in order for you to access these PDKs. So for those who are not familiar with chip design, the PDK is like the Lego blocks, like Katya was showing. So they're basically building blocks, like templates that the Foundry has already verified that they work, and then you can use them in your circuits. What does GDS Factory Plus offer you? So it will offer you design capabilities, like such as the one shown here. This is a circuit level simulation, as well as verification to make sure your chip is correct. Like, how do you know if your chip is correct? You have to do DRC, which is to make sure it's manufacturable, and LBS, to make sure that your design intent matches your layout. What do we do with GDS Factory Plus as a project? So we basically do things. We provide you with software tools, or we can also help you migrate from other tools into GDS Factory, or leverage some of the tools we've developed over the years to help you do your work. So as a summary of the tool, it's basically 200 times faster than most of the other tools. It has over almost 250 components readily available for you. It has a lot of PDKs available, and we also integrate with a lot of different tools. I think we are the only tool who integrates with everyone else. Another problem we found is like, where do you store your data? It's also because we've been in many companies where we had the same problem. Like we were like this engineer. Like I've been into a lot of companies where I don't know where the data is because there's already a lot of people working on the chips. Because when you make chips, you have different kinds of data. Like it goes from schematics, simulations, layouts, DRC results, yield data, measurements. All that data, it can be either properly stored in a place that everyone can access, or it basically gets lost. Or if you put it in a Google Drive, you still don't have the relationship between the data. Like, is this GTS? Does it have a measurement? Does it have a simulation? What is the data? So we made this platform called Do Data that allows you to integrate all the chip design data into one single place. So it provides you with a database as well as a UI, like a visualization. So you can go all the way from design, layout, verification, fabrication data, validation from the testing, as well as qualification as you go through the product life cycle. It looks kind of like this. You have a dashboard where you can visualize the data. And we have two views. We have the dashboard view, where you can do everything through the web, like it is all web-based. Or you can also do everything through a Python library that you can control from your computer. So you can pip install it, and you can start triggering analysis, storing the analysis, do analysis, aggregated analysis to do like device, die, wafer, or lot. So you can do any kind of device level analysis or any kind of aggregated analysis. So this is kind of like the summary slide. I wanted to do a demo so that we have some time. So basically, there's two things. So there's the GDS Factory, which focuses on design and verification of the circuits. And then we have the Do Data, which makes sure that you can capture all the data that you accumulate from the design to the verification, as well as the validation and testing and qualification of your products. If you have any questions, you can contact us, or you can also go to gdsfactory.com, and then you can see some of the videos of the tools that we made. Any questions before the demo, or we can also do questions after the demo? Demo? Okay. Okay, so I'm going to demo the GDS Factory Plus first. So I have it here open. This is just a lattice filter. So it's a two-stage filter where I have two Mach senders connected with each other. One of the things it allows you to do is like I can do actually simulations directly from here. So you can see it's very fast. I just click simulate and I have the simulation ready. Just to make sure like I'm not just doing anything weird, I'm going to zoom here on this MZI and I'm going to double the length. So here I'm going to make from 10 to 20. I save. I don't know if you guys noticed, but the length double, the delta length. And I'm going to run simulation again, and I simulate it, and boom, the FSR is different. So just to give an idea of the capabilities of the tool. Another thing it will allow you to do is you can also do automatic routing. So for example, a lot of times you're connecting different chiplets with each other. So you want to be able to move instances, like for example, I'm moving this instance, and the route will automatically adapt. So you can do it as many times as needed. So you have a schematic where you can define your circuit, run simulations, and then you have also automatic routing capabilities for very complex circuits. So yeah, and here you have your project components on the left. On the bottom, you have also your Foundry components. So this is with the Cornerstone Foundry that's open access. That way we can show all these demos without checking people's NDA. So yeah, and you can see also the Foundry PDK elements. Like for example, a die or anything. And this is all interactive, and you can click with it. And the other thing I wanted to show you is the do data live. So we have here a few projects. So you can see if you have wafers, you can see the wafers. You can see the cells. You can visualize the layout. Like a lot of times, you don't even, if you work in a team, like what was the layout that we sent? Or especially if you did it like 6 months ago, what was the layout? You can also see the individual cells, so you can see things like attributes of the cell. You can actually see the GDS of the cell. This is very important because a lot of times the people doing testing are not the same ones doing the design. So it helps you like connect things together. So I can see all the raw measurements as well. Like here, you can click on it and response. You can trigger an analysis on the data and like any analysis that you want. Here I'm going to do IV. You can upload your own analysis. Oh, this one may have a problem. Sorry, yeah, live demos are always. Yeah, you can upload your code, and it will automatically run an analysis for you, and then you can see the results there. So this is a device level, but a lot of times what you care about is like the die or wafer or lot. So let me go back to home. I'm going to click here on the wafers, and I can see all the individual dies, and I can see the wafer. So this is the wafer yield. So if you use like equipment manufacturing, you are going to need to step over all these reticles in the wafer and measure them individually to know which ones you need to package. In this case, we have 2 bad dies, and then you can always click on them and see what happened. Or you can also click on one of the good ones and see that all the fits were correctly done. So these are all analysis that as you were uploading the measurement, they were being fitted. And then the other thing you can also do, you can do all the way to a lot. So compare like sheet resistance, for example. I'm going to remove the outliers. And here I have like 20% variability of 3 wafers. And you can click on them and see particular wafer, what's the sheet resistance spread. So yeah, I show you the tools live. So in summary, we have shown like chip design software for like making chip design accessible to everyone, very easy to use, very fast. And then we show you another piece of software that will help you manage and organize your data so you can actually make better chips and hopefully come here and present them sometime. And thank you very much. And yeah.
Thank you. Thank you very much, Joaquin. Very dynamic presentation. So as you. So, any questions from the audience? Do you want to see any other example, or from the dynamic part? So.
Yeah.
Thank you, Joachim, for this great presentation. I think this Do Data seems like a super tool to have. I was wondering, are the data stored in the cloud, or do you have solutions where you can keep your own data? Or
yeah, that's a very good question. I actually have a slide to show it. Basically, so we provide you the software, and you are responsible for installing it wherever you want. So you can install it on your local computer, but then it defeats a bit of the purpose of the tool, because you want to put it in a shared server. So most of our customers, they put it on their own cloud. So, or you can even put it in a local server. The problem with a local server is that no matter how big your local server is, you will fill up the space. So you probably need to buy like a NAS or something where you can increase the hard drive space. But most of our customers, we recommend installing in the cloud, like Google, AWS, or we also have other clouds that we work with. That way you get unlimited space in the cloud. But yeah, there's like 4 parts. So there's the database that basically stores the relationships. There's the file storage where you store the measurement, simulation, analysis. And then you have the compute. So to run this analysis, you need some compute. Once you trigger the analysis, you need to look at the data and then process it and create new data. And all this, we have an installer that will basically install it for you.
That's great. I think coming from where I'm coming from, we would want to have as much of our own measurement data and stuff stored locally, right? Yeah. And not out of concern for confidentiality also for our clients and these things. But
yeah,
sounds like it's possible to do it.
Yeah, most foundry, we can even do like air gap server. So we have the software in a way that it doesn't need to even have the internet. So we work with from small companies to big fabs. So yeah, we're happy to provide you.
Thank you.
Okay, if there are no more questions, we can thank
Thank
Joaquin again and all the speakers of this session.
So now Pascual will close the event, and we will move on to the last lunch of the Congress. And thank you to all the speakers again of this last session.
Okay, so thank you, Gloria. Thank you all the speakers from these sessions. So yeah, we came to an end, one year more. So it is just a few slides to thank so the different participants. First of all, sponsors and exhibitors that in a big part make this happen. So thank you all. We're going to be clapping like several times. Okay, so let's thank speakers. So then there is this group of people that does the many things that we do in research. So I can't not name a thing that we don't do in the university. We do a lot of things. But so this edition, we also discovered that we can do coffee breaks. So yesterday we had an issue with the coffee break, and we did a coffee break. So because of the help of these very, very nice people. So let's thank them again. And then, of course, this is not possible without all of you coming from very distant places. In some cases, we saw the slide from the fellows from Norway. You didn't drive, right? So, okay, thank you. Thanks for the confirmation. So it's been great to hosting you here and having you. And I think that the pictures represent the spirit of the event, which is to get together in a very cozy place, not too large place, so we can have the opportunity to talk left and right to everybody. So we have been, we had, I checked just a few minutes ago, 127 registered people. It is true that a large part of them are from our own group and local people. That is true, but still it's a very good number of people. And the event is somehow manageable and still cozy, as I said, for us to be able to interact with each other. So this clapping goes for all of you, of course. And then every single year you push us a little bit further. So last year we booked the day after. So this year we book the week before. Okay, so last week we booked the date for the next year. This year we already checked the Mobile World Congress date. Sorry for you know the conflict in this edition. So we will be moving to the last week of February 2026, still starting on Monday afternoon, then Tuesday and Wednesday we like that, and that has been working. And I won't take much time from you. I will welcome you for lunch, and yeah, that's all.